For thousands of years, humanity has wrestled with one of the most profound questions. Where did the universe come from? Now, standing at the forefront of modern science, we find ourselves closer than ever to unlocking this ancient cosmic riddle. The event that sparked it all, the Big Bang, occurred around 13.8 billion years ago. At that moment, everything we know, space, time, matter, and energy, erupted into existence in a staggering explosion. But what exactly triggered this dramatic birth? What lay before that unimaginable beginning? In this documentary journey, we will dive deep into the latest scientific breakthroughs, revolutionary theories, and compelling evidence that aim to illuminate the origins of our universe. We will explore not only the explosive event itself, but the profound mysteries that surround it, guiding you through the history of discovery, the brilliant minds behind the ideas, and the cosmic fingerprints left behind. The Big Bang Theory stands today as the cornerstone explanation for the universe's origin. It tells us that the cosmos began as an incredibly hot and dense point, a singularity, from which all matter and energy expanded outward rapidly. This expansion did not stop. It continues even now, stretching galaxies farther and farther apart. Evidence for this ongoing growth comes from the way distant galaxies appear to be moving away from us, their light stretched into longer, redder wavelengths, a phenomenon called redshift. In the immediate aftermath of the Big Bang, the universe was a seething cauldron of extreme temperatures and unimaginable densities. Within this cosmic furnace, fundamental particles like protons, neutrons, and electrons emerged. As the universe expanded and cooled, these particles began to coalesce into simple nuclei. But it took nearly 400,000 years for the cosmos to cool enough for electrons to join with nuclei, forming the first stable atoms, mostly hydrogen and helium. This transformation freed photons, or light particles, allowing light to travel across space unimpeded. The leftover glow from this era is what scientists call the cosmic microwave background radiation, an ancient afterglow that fills the universe uniformly to this day. This faint microwave radiation is one of the strongest pillars supporting the Big Bang Theory. It provides us a snapshot of the universe when it was only a toddler in cosmic terms, revealing conditions consistent with an extremely hot and dense birth. The patterns and uniformity of this radiation have been measured meticulously, matching predictions made decades ago by theoretical physicists. Further strengthening the Big Bang model is the observed abundance of the universe's lightest elements. Scientists have detected precise ratios of hydrogen, helium, and lithium scattered throughout space, ratios that align perfectly with calculations from the Big Bang nucleosynthesis model. This model describes how the first nuclei formed in the earliest moments after the explosion, giving us a powerful window into the infancy of our cosmos. Tracing the roots of the Big Bang Theory leads us back to the early 20th century, to a Belgian priest and astronomer named Georges Lemaitre. In 1927, combining Einstein's groundbreaking general theory of relativity with astronomical observations, Lemaitre proposed that the universe was expanding from an initial primeval atom, a singular starting point for all existence. Although revolutionary, his ideas initially struggled for acceptance. It wasn't until the 1930s when American astronomer Edwin Hubble provided crucial evidence that the universe was indeed expanding. By observing galaxies and measuring their redshifts, Hubble demonstrated a direct relationship. The farther away a galaxy is, the faster it moves away from us. This discovery confirmed Lemaitre's hypothesis and transformed it into the foundation of modern cosmology. Interestingly, the name Big Bang was coined much later, in 1949, during a BBC radio broadcast by British scientist Fred Hoyle. Hoyle favored a competing theory called the steady-state model, which suggested that the universe had no beginning and remained constant on a large scale. Ironically, his use of Big Bang to mock the idea ended up popularizing the very concept he opposed. Over the decades, advances in technology and observations, such as the detection of cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson, solidified the Big Bang Theory as the leading explanation for our universe's origin. Their discovery provided a clear, measurable echo from the universe's fiery infancy, aligning perfectly with theoretical expectations. Together, these lines of evidence form a rich tapestry of knowledge, pieced together by scientists across generations. From the expanding galaxies to the primordial light elements to the faint microwave glow from the dawn of time, the universe continues to tell its story. Each discovery deepens our understanding, moving us closer to answering that fundamental question. What caused the Big Bang? While many mysteries remain, the journey of exploration reveals the incredible power of human curiosity and the enduring quest to comprehend our cosmic beginnings. Moreover, the redshift of distant galaxies offers compelling evidence in support of the Big Bang theory, a cornerstone of modern cosmology. When Edwin Hubble first observed that galaxies are receding from us, he discovered something remarkable. The farther a galaxy is from Earth, the faster it appears to be moving away. This observation wasn't just a random coincidence. It revealed a profound truth about the nature of our cosmos. It pointed to an expanding universe, one that is not static but dynamic, growing larger over time. This expansion implies that the universe must have had a beginning, a moment when all of space and time emerged from an extremely hot, dense, and compact state. That moment is what we now call the Big Bang. The implications are profound. Rather than existing forever in its current form, the universe had an origin and has been stretching out ever since. The large-scale structure of the cosmos today, spanning galactic clusters, superclusters, and vast filamentary webs, adds another layer of confirmation. High-powered simulations based on the Big Bang framework demonstrate how such structures could emerge naturally. These models start with tiny fluctuations in density in the early universe, imperceptible but crucial, and show how, over billions of years, they evolved into the sprawling galactic architecture we now observe through telescopes. What once seemed chaotic and unformed has matured into an intricate cosmic tapestry. Taken together, these observations, the redshift of galaxies, the cosmic expansion, and the observed structure of the universe, create a powerful, interconnected body of evidence. Each piece reinforces the others, forming a coherent picture that aligns with the Big Bang theory as the most widely accepted explanation for the origin and evolution of the universe. According to this theory, the age of the universe is estimated to be about 13.8 billion years. This figure is not based on a single observation, but arises from several independent lines of investigation. One of the most precise methods involves analyzing the cosmic microwave background radiation, a faint glow left over from the early universe. Space missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite have measured this radiation in extraordinary detail, uncovering minute fluctuations in temperature across the sky. These temperature variations carry the imprint of the universe when it was just 380,000 years old, when it first became transparent to light. From this information, scientists can deduce how long the universe has been expanding. Another major piece of evidence comes from observing the redshifts of galaxies. By measuring how fast galaxies are moving away from us and how far they are, astronomers can estimate how long the universe has been expanding. Central to this is the Hubble constant, which quantifies the rate of expansion. When this rate is traced backward, it aligns with the 13.8 billion year estimate, providing consistency across very different forms of measurement. Yet another method involves studying the oldest stars in our galaxy, the Milky Way. These ancient stars, some of which are over 13 billion years old, serve as natural clocks. Using stellar evolution models, scientists can estimate their ages with surprising accuracy. These estimates offer a lower limit for the universe's age, and once again, they closely align with findings from other methods. So, through diverse and independent means, radiation from the early universe, the motion of galaxies, and the age of ancient stars, scientists have converged on a singular, awe-inspiring conclusion. The universe is about 13.8 billion years old. It's a number that encapsulates an epic journey from a fiery origin to the magnificent structured cosmos we witness today. In the moments just after the Big Bang, the universe was in an almost unimaginably hot and dense state. Everything, matter, energy, even the fabric of space and time itself, was compressed into an infinitesimal point known as a singularity. Temperatures during this period reached trillions of degrees. At such extreme levels of energy, no atoms or stable matter could exist. Instead, the universe was a seething, chaotic soup of fundamental particles, quarks, electrons, and other basic building blocks of matter. This initial period is known as the Planck epoch. It lasted for only a fleeting instant, just 10 to the power of minus 43 seconds. During this time, the known laws of physics break down, and quantum effects dominated. Almost immediately after this epoch, the universe underwent a dramatic phase known as cosmic inflation. In this phase, the universe expanded at an exponential rate, smoothing out any irregularities and setting the stage for the structure that would later emerge. As the universe cooled, quarks began to bond together to form protons and neutrons. Within the first few minutes, a period called the era of nucleosynthesis, conditions stabilized just enough to allow these protons and neutrons to combine into the first atomic nuclei. Hydrogen and helium were formed in abundance along with trace amounts of lithium. These light elements still dominate the universe today. However, during this time, the universe remained opaque. It was filled with a dense plasma, and photons, particles of light, could not travel freely. That changed about 380,000 years after the Big Bang. The universe had cooled enough for electrons to combine with nuclei, forming neutral atoms. This pivotal moment, known as the recombination era, allowed light to move through space unimpeded for the first time. The radiation released then still exists today as the cosmic microwave background, a silent whisper from the infancy of the cosmos. From that transformative moment, the universe began its long journey toward complexity. Galaxies formed, stars ignited, and planets coalesced. What began as a turbulent, high-energy flash has given rise to the majestic cosmic structure we now call home, a testament to the enduring power and elegance of the Big Bang theory. Cosmic microwave background radiation stands as one of the most profound and compelling pillars of evidence supporting the Big Bang theory, revealing the very infancy of our universe. This faint, almost whisper-like glow permeates the entire cosmos, acting as a relic from the earliest moments after the universe burst into existence. To understand its significance, we must journey back nearly 14 billion years, to a time when the universe was an incredibly hot, dense, and turbulent plasma, a chaotic soup of particles so energetic that light itself could not travel freely. In those first instants, the universe was opaque, a vast fog where photons, the particles of light, were constantly scattered by free electrons. But as the universe expanded, it cooled steadily, gradually allowing the particles to slow down and combine. About 380,000 years after the Big Bang, a mere blink in cosmic terms, the universe reached a crucial milestone. Atoms formed, mainly hydrogen and helium, creating a transparent medium where photons could finally break free. This event, known as the decoupling of matter and radiation, unleashed a flood of electromagnetic waves, bathing the cosmos in light. Originally, this radiation was blisteringly hot and intensely energetic, emitting primarily in the visible and ultraviolet ranges. Yet, as billions of years passed and the universe continued to swell outward, the wavelengths of this primordial light stretched and cooled dramatically, shifting from the realm of visible light into the microwave portion of the electromagnetic spectrum. Today, scientists detect this ancient radiation as a nearly uniform background glow at a temperature just about 2.7 degrees above absolute zero. 7 degrees Kelvin, covering the sky in every direction. The remarkable uniformity of this cosmic microwave background, CMB, is a cornerstone for the idea that the universe began as a hot, dense point and has been expanding ever since. But it is not only the uniformity that intrigues cosmologists. Subtle fluctuations in this radiation reveal tiny temperature variations, mere fractions of a degree, spread across the sky. These minuscule irregularities represent the seeds of cosmic structure, tiny density differences in the early universe that, over billions of years, grew under the influence of gravity into the vast tapestry of galaxies, clusters, and superclusters that define the large-scale structure of the cosmos today. By carefully studying the patterns of these fluctuations, scientists extract vital information about the universe's expansion rate, its overall shape, and the proportions of matter and energy it contains. Missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have taken measurements of the cosmic microwave background to unprecedented precision. Their data has not only confirmed the fundamental predictions of the Big Bang theory, but also refined our understanding of the universe's age, the speed of its expansion, and the abundance of elements forged in the early cosmic furnace during nucleosynthesis. In essence, the CMB serves as a cosmic blueprint, a fossil record etched in the fabric of space-time that chronicles the universe's birth and evolution. But the story does not end there. To solve some lingering mysteries that the classical Big Bang theory couldn't fully address, scientists proposed the theory of cosmic inflation, a mind-boggling idea describing a brief explosive expansion of the universe within an unimaginably tiny fraction of a second after the Big Bang, during the so-called Planck epoch. According to this theory, the universe inflated exponentially, swelling from subatomic dimensions to nearly the size of a galaxy in less than a billionth of a second. This rapid inflationary burst elegantly explains why the cosmic microwave background radiation is so strikingly uniform across the sky. Without inflation, regions of the universe separated by vast distances would never have had the chance to exchange information or equilibrate their temperatures, leaving the CMB inexplicably patchy. Inflation suggests that before this rapid expansion, the universe was incredibly compact, allowing these distant regions to interact and settle into a nearly identical temperature and composition. Beyond explaining uniformity, inflation also provides a natural origin for the large-scale structure of the cosmos. During this fleeting period, quantum fluctuations, tiny random variations at the smallest scales, were stretched to enormous sizes, imprinting subtle irregularities onto the fabric of space itself. These stretched quantum ripples formed the primordial seeds of density variation, eventually growing under gravity to become the galaxies, clusters, and cosmic web we observe through our most powerful telescopes. In this way, cosmic microwave background radiation and the theory of cosmic inflation weave together a mesmerizing narrative of our universe's origin, a fiery birth, a rapid inflationary growth spurt, and the gradual formation of all the magnificent structure we see today. These discoveries transform what once seemed like an empty sky into a detailed historical record, allowing us to peer back in time and glimpse the universe's earliest moments, its evolution, and its extraordinary vastness. Arising from the initial uniformity of the universe, cosmic inflation theory has transformed our understanding of the cosmos in profound ways. Furthermore, cosmic inflation predicts that the universe may be flat, possessing a specific geometry determined by the total density of matter and energy within it. Observations, particularly from the cosmic microwave background radiation, the faint afterglow of the Big Bang, have provided strong evidence supporting the concept of a flat universe. These findings align remarkably well with the predictions of inflationary models. This groundbreaking theory does more than explain the universe's geometry. It also offers a compelling explanation for the mysterious cosmic acceleration observed in recent decades. Scientists suggest that scalar fields, which once drove the rapid expansion during inflation, could still be subtly influencing the universe's expansion today. This insight adds a fascinating layer to our cosmic story, linking the universe's earliest moments to its ongoing evolution. Overall, cosmic inflation enriches our grasp of the early universe by providing a comprehensive framework that addresses several key cosmic puzzles. It explains the striking uniformity of the cosmic background radiation, the formation of large-scale structures such as galaxies and clusters, and the very shape of the universe itself. By doing so, inflation enhances the explanatory power of the Big Bang theory, deepening our insight into how the cosmos unfolded from its earliest fractions of a second. Another crucial piece of evidence supporting the Big Bang theory lies in the abundance of light elements found throughout the universe, particularly hydrogen, helium, and lithium. This abundance emerges from a process called Big Bang nucleosynthesis, which took place within the first few minutes after the Big Bang. During this time, the universe was a seething furnace of extreme temperatures and pressures, enabling protons and neutrons to combine and form atomic nuclei. According to the predictions derived from Big Bang nucleosynthesis models, about 75% of the universe's ordinary matter should be hydrogen, roughly 25% helium, and trace amounts of lithium and deuterium. Observations of the primordial abundances of these elements across the cosmos consistently match these predictions with remarkable accuracy. For example, the ratio of helium to hydrogen observed in ancient stars and distant gas clouds aligns almost perfectly with what the Big Bang theory forecasts. This strong agreement reinforces the idea that the early universe itself forged these elements during its nucleosynthesis phase. The measured abundances of these light elements offer a unique window into the conditions of the primordial universe. When astronomers study the composition of old stars and interstellar gas clouds, they find that the relative proportions of these elements reflect the predictions made by the Big Bang theory. The widespread uniformity of these elements throughout the cosmos suggests they all originated from the same early processes, further confirming their cosmic origin. Moreover, the study of these light elements goes beyond simply measuring their abundance. The presence and distribution of isotopes like deuterium and lithium provide additional layers of evidence that help scientists refine their understanding of the universe's expansion rate and overall density. Occasionally, discrepancies between observed amounts and theoretical predictions challenge existing models, driving new research and improvements to the Big Bang framework. Collectively, the observed abundances of light elements serve as robust pillars supporting the Big Bang theory. They illustrate a clear, traceable connection between the universe's earliest moments and the cosmic chemical landscape we observe today. When scientists refer to T equals 0 in the context of the Big Bang, they are describing the moment when time itself, as we comprehend it, began. This point represents the very beginning of the universe, when all matter, energy, and the very fabric of space and time were compressed into an unimaginably hot and dense state. The label T equals 0 marks a boundary beyond which our current physical theories cannot reliably describe conditions or events, as the known laws of physics break down under such extreme circumstances. At this singular moment, the universe was not only incredibly hot and dense, but is also believed to have contained all the fundamental forces of nature: gravity, electromagnetism, and the nuclear forces, in a unified state. As the universe expanded from this initial singularity, it underwent a series of dramatic transformations, cooling rapidly and causing these forces to separate into the distinct interactions we observe today. This moment marks the dawn of the universe's evolution, setting in motion the processes that eventually gave rise to galaxies, stars, planets, and all cosmic structures we see around us. It is essential to understand that T equals 0 is not a precise timestamp that can be measured or experimentally verified. Instead, it highlights the limits of our current understanding. It challenges our intuition because time itself did not exist before this instant. There is no before the Big Bang, as time began with it. The transition from T equals 0 to the early stages of the universe lays the groundwork for everything that followed, including cosmic inflation, nucleosynthesis, and the formation of atoms and galaxies. This phrase captures the profound complexities of cosmology as scientists strive to unravel the history of the cosmos from this mysterious starting point onward. While many questions remain unanswered about the very beginning of everything, T equals 0 remains a crucial cornerstone for understanding the origins and evolution of the universe that surrounds us today. And yet, the question persists: what existed before the Big Bang? It is a question that rests at the edge of human understanding, where science meets the unknown and the boundaries of time and space dissolve. To ask what came before the beginning is to challenge the very framework of reality as we understand it. According to the prevailing cosmological model, the universe began approximately 13.8 billion years ago in an event known as the Big Bang. At that moment, the universe existed as an unimaginably hot, dense state, a singularity where the known laws of physics break down. From this singularity, time and space themselves are believed to have emerged, and herein lies the dilemma. If time itself began with the Big Bang, can we truly speak of a before? Many physicists and cosmologists argue that the concept of before the Big Bang may be fundamentally flawed. In a universe where time has a starting point, the notion of a prior state may have no physical meaning. It is like asking what is north of the North Pole. Time, in this context, did not exist, so the very idea of something preceding the universe becomes slippery, perhaps even meaningless. Still, human curiosity refuses to be confined. Theoretical physics offers glimpses into possibilities that extend beyond the Big Bang. Among these are proposals of a cyclic universe, a cosmos that expands, contracts, and rebounds in an infinite rhythm. In this view, the Big Bang may not have been the beginning of everything, but rather a transitional event in an endless cosmic dance. Other models suggest a multiverse, a vast, possibly infinite ensemble of universes, each with its own laws of physics, timelines, and origins. In the framework of string theory, dimensions beyond the familiar three of space and one of time may house parallel realities, forever inaccessible yet profoundly intriguing. The mathematics is compelling, but the evidence remains elusive. Eternal inflation, one of the most provocative ideas to emerge from modern cosmology, takes this even further. Building upon the concept of cosmic inflation, which describes a brief but exponential expansion of the universe fractions of a second after the Big Bang, eternal inflation suggests that this process never truly stopped. Instead, while inflation may have ended in our region of space, other regions continue to inflate endlessly. Each cessation creates a new bubble universe, complete unto itself, governed by its own physical parameters. In this model, our universe is but one bubble in a cosmic foam of infinite potential. These bubbles, each a universe in its own right, could vary wildly. Some with gravity stronger or weaker than ours, some with no matter at all, some perhaps incapable of supporting complexity or life. The driving force behind this inflationary expansion is theorized to be a scalar field, commonly referred to as the inflaton. Depending on its energy state, regions of space may expand rapidly or cool and settle into more stable configurations. It is a process that could, in principle, go on forever. The implications are staggering. Not only could eternal inflation explain the uniformity and smoothness of our observable universe, but it also introduces a cosmic lottery, a landscape of possibilities where everything that can happen does happen somewhere. And yet we face a monumental challenge. How does one test such theories? By their nature, these ideas are extraordinarily difficult to confirm through observation. We are bound within our bubble, and even the most powerful telescopes can only peer so far. Multiverses and pre-Big Bang scenarios may remain forever outside the reach of empirical science. Then again, science has never been static. With each technological leap, new windows into the cosmos open. Gravitational wave astronomy, quantum field theory, and refined models of cosmic background radiation all hold promise for deepening our understanding. One day, we may find indirect evidence, subtle imprints perhaps, left over from a universe that came before, or hints of other worlds beyond our own. The idea of a cyclic universe also refuses to fade. In some models, the universe doesn't expand forever. After reaching a maximum size, it contracts, collapsing into a big crunch, a dense, hot state not unlike the one that birthed it. From that collapse, a new Big Bang might erupt, starting the cycle anew. In this vision, the universe has no true beginning or end, only cycles without origin. These concepts are not without precedent. Ancient philosophies and mythologies have long envisioned time as circular, not linear. Now, science finds itself entertaining similar ideas, not because of poetic resonance, but because the mathematics allows for it. What came before the Big Bang? The honest answer is, we do not know. But the very pursuit of that answer is reshaping our understanding of reality. In seeking what lies beyond the veil of the known universe, we are not merely probing the beginning of time, we are questioning the nature of existence itself. If these ideas prove true, we may discover that our universe is just one verse in a grand cosmic symphony, echoes from a realm where time, space, and reality itself are far more mysterious than we ever imagined. One of the most profound challenges that the cyclic universe theory poses to the widely accepted Big Bang model revolves around how we understand time and the very essence of the cosmos. The Big Bang theory paints a picture of the universe with a clear starting point, approximately 13.8 billion years ago, when everything as we know it burst into existence from an unimaginably dense and hot singularity. In contrast, the cyclic universe model proposes a radically different narrative. The universe is eternal, endlessly cycling through phases of birth, death, and rebirth. This perspective forces us to reconsider foundational questions about the origin of matter, energy, and the fundamental laws that govern reality, suggesting that the universe we observe today is simply one chapter in an infinite, ongoing story. Delving deeper, The cyclic model introduces a striking possibility. With each cycle, the conditions of the universe could shift, potentially altering physical constants or the fundamental forces that shape existence. Imagine that one cycle might produce a universe with different rules of physics than the last. Perhaps even a universe so distinct it feels alien to us. This fluidity opens the door to explanations for puzzling features of our own cosmos, such as the remarkable uniformity seen in the cosmic microwave background radiation, the faint afterglow of the universe's earliest light. These patterns might arise from the mechanisms governing the transitions between cycles, offering clues that each phase leaves an imprint on the next. Yet, despite its allure, the cyclic universe theory remains speculative, wrestling with formidable scientific challenges. One major hurdle lies in explaining how the universe switches from expansion to contraction, and whether a catastrophic event, like the Big Crunch, could seamlessly trigger another Big Bang without rewriting the fundamental laws of physics. The debate among cosmologists and physicists continues vigorously, as this model demands new ways of understanding the past, present, and future of the cosmos, offering tantalizing possibilities, but no definitive answers yet. Closely related is the Big Bounce theory, a cosmological idea that reimagines the universe not as having a singular explosive origin, but as undergoing a rhythmic cycle of expansions and contractions. Instead of a singular birth event, the Big Bounce suggests that our universe bounced back from a previous contraction phase, entering into the current expansion that we observe today. This cyclical bouncing could, in theory, continue indefinitely, with no clear starting point marking the beginning of time itself. The Big Bounce idea arises from advances in quantum gravity, modifications to Einstein's classical theory of general relativity, that allow physicists to describe extreme conditions where densities skyrocket to unimaginable levels. Rather than collapsing into an infinite density or singularity, the universe passes through a quantum phase where the traditional laws of physics transform, enabling a rebound. This quantum bounce effectively resets the cosmos, sparking a fresh expansion phase that resembles the familiar Big Bang, but without the paradox of an absolute beginning. One of the greatest strengths of the Big Bounce theory is its ability to sidestep some of the conceptual puzzles posed by the Big Bang singularity. The initial singularity challenges scientists: what was before the Big Bang, and how could anything exist at infinite density? The Big Bounce offers a smoother narrative, portraying the cosmos as eternal and cyclic, which opens avenues for understanding its evolution as a continuous process rather than a one-time event. Still, the theory faces its own obstacles. Scientists are working to pinpoint the exact mechanisms behind the contraction to expansion transition, and to connect predictions from the model with observable evidence in our current universe remains a daunting task. Beyond cyclic and bouncing models, string theory offers a radically different approach to the origin and nature of everything. Rather than viewing the universe as built from point-like particles, string theory envisions the fundamental constituents as tiny, vibrating strings, so small that their size is beyond the reach of current experiments. These strings can take the form of closed loops or open strands, and their vibrations correspond to the particles we know, such as electrons and quarks. This framework is revolutionary because it attempts to unify quantum mechanics with general relativity, bridging the largest and smallest scales of the cosmos and potentially answering deep questions about the universe's birth. A striking feature of string theory is the proposal of extra dimensions beyond the familiar 3 dimensions of space and 1 of time. These additional dimensions, hidden from everyday experience, could hold the key to unifying the fundamental forces of nature, explaining why gravity is so much weaker than electromagnetism, for example. The shapes and configurations of these extra dimensions might influence how strings vibrate, which in turn affects the properties of particles and forces during the universe's earliest moments. Thus, these unseen dimensions could have played a crucial role in shaping our cosmos. String theory also introduces the concept of the string landscape, a vast array of possible ways the extra dimensions might be configured, each giving rise to different physical laws. Within this landscape, our universe could be just one among countless others, each with its own unique characteristics and constants, a multiverse of sorts. This idea not only broadens our understanding of the universe's creation, but also suggests the potential existence of many other universes, vastly different from our own. Together, these theories, the cyclic universe, the Big Bounce, and string theory, challenge the traditional Big Bang model, each offering intriguing new perspectives on cosmic origins. While none have yet achieved consensus, they expand the boundaries of human inquiry into the cosmos, inspiring scientists to explore the profound mysteries of time, space, and existence itself. As research advances, we may find that the universe's story is far richer and more complex than previously imagined, a tale of cycles, bounces, and vibrating strings weaving the fabric of reality. And yet, buried deep within the intricate framework of modern theoretical physics lies a captivating idea, one that defies not only our current understanding of space and time, but also the very limits of the observable universe. In some versions of string theory, a revolutionary perspective takes hold. The universe may not be the only one. Hidden within higher dimensions, vast cosmic surfaces called branes serve as the stage on which the tiny vibrating filaments known as strings reside. These branes are not passive. They move, they shift, and according to certain string theory models, they can even collide. When two of these colossal, multidimensional entities smash together, they could unleash an immense burst of energy, an event akin to a second Big Bang. This cosmic upheaval, born from the interaction of higher dimensional branes, may mirror the inflationary period believed to have occurred shortly after our own universe came into being. The rapid expansion triggered by such a collision could sculpt a new universe with its own physical properties, perhaps not unlike the one we inhabit. String theory paints an awe-inspiring picture of the cosmos, threading together quantum mechanics and general relativity in a pursuit to reveal the grand design of reality. But for all its beauty and mathematical elegance, it remains a theoretical frontier. The fundamental particles it describes, tiny strings vibrating in 10 or 11 dimensions, are so minuscule, so deeply embedded in the fabric of existence that they elude direct observation. Current technologies fall short of the scale needed to detect them, making empirical confirmation a challenge of nearly unimaginable proportions. Still, physicists press on. Through experiments in particle accelerators, astronomical observations, and bold theoretical innovations, scientists continue to probe the universe, seeking subtle clues that might elevate string theory from speculative brilliance to observable truth. And string theory is just one piece of a much larger cosmic puzzle. Consider the idea of the multiverse, the possibility that our universe is but one among countless others. It's a concept that reshapes our understanding of everything. Each universe within the multiverse may operate under different rules, governed by its own laws of physics, constants, or even dimensional structures. These alternate realities might contain forms of matter, energy, and life that are wholly alien to our own. Where does this concept originate? In part, it's born from inflation theory, which suggests that the universe experienced a phase of rapid expansion in its earliest moments. During this period, different regions of space could have inflated at different rates, becoming isolated from one another, resulting in a sprawling cosmic foam, with each bubble representing a unique universe. These bubbles are causally disconnected, forever separated by the ever-expanding fabric of space-time. Some physicists propose that as our universe stretched and evolved, gaps may have opened in the vacuum of space, gateways to other universes forming in adjacent bubbles. These could differ so drastically in structure that they challenge our very understanding of reality. Imagine a universe where time flows backward, or where gravity is a repulsive force rather than an attractive one. The multiverse theory opens the door to such possibilities. It also raises profound philosophical questions. If there are infinite universes, what makes ours special? Or is our world simply one random outcome among an endless array of variations? While definitive proof remains elusive, the multiverse continues to fuel speculation, pushing the boundaries of science and philosophy alike. And within this speculative realm lies a smaller yet equally astonishing phenomenon: quantum fluctuations. At the heart of quantum mechanics lies uncertainty, specifically the Heisenberg uncertainty principle. It tells us that certain properties of a particle, like its energy and position, cannot both be precisely known at the same time. This fundamental ambiguity means that even empty space isn't truly empty. Instead, it teems with activity. Tiny jolts of energy spontaneously emerge and vanish, giving rise to what we call quantum fluctuations. These fleeting disturbances played a pivotal role in the early universe. When the cosmos was still unimaginably hot and dense mere moments after the Big Bang, quantum fluctuations created minuscule differences in energy distribution. These microscopic irregularities served as the seeds for all large-scale structures in the universe. Over billions of years, gravity amplified them, shaping galaxies, stars, and ultimately the planets we know today. But quantum fluctuations aren't just historical relics. They remain ever present in what physicists refer to as vacuum energy, the baseline energy of space, even when devoid of matter. Here, virtual particles constantly pop into and out of existence, a ceaseless quantum dance that reshapes our concept of emptiness. These fluctuations hint at a deeper, more dynamic reality, one where the building blocks of the cosmos arise not from solidity, but from uncertainty. They are reminders that the universe operates on levels we are only beginning to comprehend, where the smallest interactions ripple outward to influence the grandest structures. As research advances, scientists continue to explore these hidden patterns, string vibrations, cosmic collisions, bubbling universes, and the ghostly flicker of particles in the vacuum. Each discovery nudges us closer to understanding the true nature of reality. And in doing so, we are reminded that the universe may be far more vast, strange, and beautiful than we ever imagined. And yet, from what seems like nothing, utter emptiness, came everything. In the first fleeting instance of the universe, long before stars lit up the sky or galaxies stretched across the void, the cosmos was ruled by the strange, unpredictable laws of quantum mechanics. In this earliest epoch, quantum fluctuations, tiny, random shifts in energy, played a pivotal role in sculpting the very blueprint of the universe. These fluctuations weren't just noise. They were cosmic brushstrokes painted on an unimaginably small canvas. As the universe emerged from the Big Bang, a moment of infinite density and temperature, it didn't unfold into perfect uniformity. Instead, some regions of space had slightly more energy than others. Quantum mechanics, governing this embryonic universe, allowed brief surges of energy to ripple through space-time. These variations in energy density were microscopic, yet they became the seeds of everything we see today. In the blink of an eye, a dramatic transformation occurred. Known as inflation, this phase of exponential expansion stretched space itself at a speed faster than light. What began as subatomic wrinkles in the energy field were now smeared across vast distances. The inflationary model suggests that this burst of growth smoothed out most irregularities, but crucially, it preserved the initial quantum imprints, now magnified across cosmic scales. These once-minute energy pockets became gravitational beacons, attracting more and more matter over time. As the universe cooled, the high-energy vacuum state that had driven inflation decayed, and quantum fluctuations were effectively frozen into the fabric of space-time. Matter clumped around denser regions, pulled in by gravity, and over billions of years, these early imbalances gave rise to the rich structure of the cosmos. Stars, galaxies, superclusters, and immense voids. Every massive spiral galaxy, every glimmering cluster of suns, can trace its origin to a tiny random flutter in the quantum vacuum. This intricate dance between randomness and structure reveals a profound truth. The universe as we know it was not born in order, but in chaos. The tiniest particles, governed by uncertain principles, have given rise to grand cosmic architecture. It's a staggering realization that the very laws which describe electrons and quarks are intimately linked to the formations of galaxies and the fate of the universe itself. Central to this narrative is the enigmatic concept of vacuum energy. Often misunderstood, vacuum energy doesn't imply that empty space is truly empty. On the contrary, according to quantum field theory, what we perceive as a vacuum is alive with activity. Fields permeate all of space, and fluctuations within them cause virtual particles to flicker into and out of existence. This restless activity creates a baseline energy level even in what appears to be empty space. This vacuum energy carries weight, literally. Its effects are far-reaching, influencing the universe's expansion and potentially tying into the mystery of dark energy, the unseen force believed to be accelerating that expansion. If space itself has intrinsic energy, it can stretch the universe apart, counteracting gravity and dictating the cosmos's long-term evolution. The implications are staggering. It suggests that nothingness itself can drive change on a cosmic scale. As cosmologists and particle physicists dig deeper, they continue to probe the nature of this vacuum energy. Could it be the key to understanding why the universe exists? Could it explain why matter dominates over antimatter, or hint at what came before the Big Bang? These are not just theoretical exercises, they are fundamental questions that challenge our understanding of reality. The marriage of quantum mechanics and cosmology doesn't just describe the past, it might determine the universe's ultimate fate. Will the vacuum energy grow stronger, tearing galaxies apart in a big rip? Will it fade, causing a cold, empty universe? Or might new physics yet unknown reveal a cycle of rebirth? At its core, the story of quantum fluctuations and vacuum energy reminds us that the universe is far stranger and far more wondrous than we ever imagined. It invites us to reconsider what we think we know about beginnings, emptiness, and the subtle forces that have shaped everything, from particles to planets, from the tiniest vibration in a quantum field to the largest galaxies lighting up the night sky. Additionally, vacuum energy plays a crucial role in the grand discussions surrounding the energy balance of the cosmos. Theories suggest that what we call dark energy, the mysterious force that appears to be driving the accelerated expansion of the universe, may be intimately connected to vacuum energy. If vacuum energy indeed permeates the entire cosmos, it could continue to shape and influence the universe's dynamics far beyond its origin. At the heart of this idea lies the concept of the zero-point energy field, which refers to the lowest possible energy state in a quantum system. Even at absolute zero, the coldest temperature imaginable, the field retains a residual energy. This remarkable notion arises from the principles of quantum mechanics, revealing that particles can never be completely still. Due to an inherent uncertainty in both their energy and position, particles are always in motion, even in what we consider a perfect vacuum. This means that in a space seemingly devoid of matter, energy fluctuations still occur, creating a non-zero baseline energy known as zero-point energy. On a microscopic scale, fundamental fields such as the electromagnetic field and the electron field constantly exhibit this zero-point energy. These fields remain in a perpetual state of excitation, with virtual particles fleetingly appearing and disappearing as a result of these energy fluctuations. It is important to clarify that these fields do not contain tangible particles observable by us, but rather represent a dynamic, ever-active state where energy exists even without any matter present. Zero-point energy holds significant weight in numerous physical theories, especially quantum field theory and cosmology. Within the framework of vacuum energy, it provides a foundation for understanding phenomena like dark energy, which is responsible for the universe's accelerated expansion. The zero-point energy field acts as a backdrop influencing particle behavior and even the large-scale structure of the cosmos itself. Exploring zero-point energy naturally leads to captivating questions about the possibility of harnessing this energy for practical purposes. While zero-point energy exists ubiquitously throughout the universe, extracting it remains a highly speculative endeavor, filled with enormous scientific and technological challenges. Nevertheless, this quest continues to fascinate scientists and researchers, as uncovering the deeper implications of zero-point energy could revolutionize our understanding of fundamental physics and potentially open new frontiers in energy generation, and advanced technology. Central to these discussions are virtual particles, fundamental constructs within quantum mechanics, with profound implications for our comprehension of the early universe. These particles emerge spontaneously from energy fluctuations present in a vacuum, appearing and vanishing within extraordinarily brief time intervals, all in strict accordance with the Heisenberg uncertainty principle. This principle permits temporary violations of energy conservation, allowing virtual particles to come into existence momentarily before dissolving back into the vacuum. In the context of the early universe, virtual particles would have thrived amidst the extreme heat and density prevailing just after the Big Bang. During this chaotic epoch, these particles generated transient energy fluctuations throughout the fabric of space-time. Far from a calm and empty void, The universe was a turbulent environment bubbling with energetic processes that played essential roles in cosmic evolution. The role of virtual particles becomes even more critical when considering the theory of cosmic inflation, the rapid exponential expansion of the universe immediately following the Big Bang. During this inflationary phase, quantum fluctuations influenced by virtual particles caused slight variations in energy density across space. These minute fluctuations acted as the primordial seeds from which the universe's large-scale structures, such as galaxies and clusters of galaxies, eventually grew. When the inflationary period ended, the energy embedded in those fluctuations could have fueled the growth of matter, shaping the vast and intricate cosmic landscape we observe today. Thus, virtual particles not only deepen our understanding of the early universe, but also serve as a vital bridge connecting quantum mechanics with cosmology. They illuminate how microscopic phenomena on unimaginably tiny scales can give rise to the enormous, complex structures that populate the universe. The four fundamental forces of nature are the invisible architects behind everything we see, feel, and experience in the universe. These forces govern how matter and energy interact on every scale, from the tiniest particles inside atoms to the vast cosmic web stretching across billions of light years. They are gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, each with its own unique role in shaping the fabric of reality. Gravity is the most familiar of these forces because it affects us daily. It is the invisible pull that anchors us to Earth and choreographs the dance of planets, stars, and galaxies. Despite its pervasive influence, gravity is actually the weakest of the four forces. Its power lies not in strength, but in reach. Gravity stretches across the vast emptiness of space, pulling entire galaxies together and sculpting the structure of the cosmos itself. This subtle yet persistent force is what keeps the universe bound as a whole. Next comes electromagnetism, a force that governs the interactions of charged particles. It is behind electricity, magnetism, and light, fundamental aspects of everyday life and technology. Electromagnetism is far stronger than gravity and operates over similar distances, but it depends crucially on the electric charge of particles. This force dictates how atoms form, how chemical reactions occur, and how light travels through space, bridging the gap between the microscopic and the macroscopic worlds. Then there is the weak nuclear force, a subtle yet essential player that acts only within the tiniest scales inside the atomic nucleus. It drives processes like beta decay, where neutrons inside atoms transform into protons while releasing electrons and neutrinos. Though limited to subatomic distances, the weak force is fundamental for the workings of stars, fueling the nuclear fusion reactions that light up our sun and other stars in the night sky. The strong nuclear force is the mightiest of all, but it reigns only over the smallest realms, binding protons and neutrons together in atomic nuclei. Without this force, positively charged protons would repel each other, and atoms would fall apart. The strong force acts like a powerful glue, stabilizing matter and ensuring the universe is filled with the building blocks necessary for life and complexity. These four forces do not exist in isolation. Their interplay weaves the story of everything, from the behavior of fundamental particles to the grand evolution of the cosmos. Understanding them is key to unlocking the deepest mysteries of physics and the universe's very nature. Rewinding to the earliest moments after the Big Bang, the universe was unimaginably hot and dense, a primordial soup of energy and potential. Under these extreme conditions, physicists theorize that the four fundamental forces were once unified into a single force. This idea emerges from the concept that at energy scales far beyond our everyday experience, the distinctions between forces blur, and they behave as one. This period, known as the Grand Unification epoch, happened within a fleeting instant, around 10 to the power of minus 32 seconds after the Big Bang. During this phase, the strong, weak, and electromagnetic forces fused into a unified force, while gravity remained separate due to its unique properties. As the universe expanded and cooled, energy levels dropped, causing this unification to break apart step by step. First, the combined grand unified force separated into the strong nuclear force and the electroweak force, a fusion of electromagnetism and the weak nuclear force. Later, as cooling continued, the electroweak force itself split, dividing into the distinct electromagnetic and weak nuclear forces we recognize today. Gravity, meanwhile, continued to govern space-time separately. This cosmic sequence of unification and separation reveals a profound connection between energy and the fundamental forces that shape reality. While much of this remains theoretical, ongoing research in high-energy physics seeks to uncover the intricate relationships between these forces and whether they might one day be fully unified. A pivotal chapter in this story is the electroweak force, a fusion of electromagnetism and the weak nuclear force described by the electroweak theory developed in the mid-20th century by physicists such as Sheldon Glashow, Abdus Salam, and Steven Weinberg. Their groundbreaking work showed that at extremely high energy levels, the forces governing charge-particle interactions and nuclear decay are two facets of the same fundamental interaction. The separation of the electroweak force into its components occurred roughly 1/10 of a second after the Big Bang, during the electroweak epoch. As the universe cooled just enough, the forces began to behave distinctly. Before this moment, the strong, weak, and electromagnetic forces were united under a grand symmetry. Breaking this symmetry paved the way for the universe to develop the rich structure we see today. The weak nuclear force governs processes inside atoms, like beta decay, while electromagnetism shapes the interactions between charged particles across space, giving rise to light, chemistry, and the forces that sustain life. Through this incredible story, the fundamental forces reveal themselves not as static entities, but as dynamic players whose relationships evolved with the universe's growth. Understanding their origins and interactions helps us grasp the profound unity underlying the cosmos and brings us closer to answering the deepest questions about the nature of reality itself. The electroweak theory stands as a cornerstone in the standard model of particle physics, offering a comprehensive framework that unravels how particles interact through fundamental forces and reveals the intricate properties governing their behavior. This theory unifies the electromagnetic force and the weak nuclear force into a single electroweak force, providing critical insights into the fabric of the universe. By studying how the electroweak force separates into its components, scientists gain invaluable clues about the universe's earliest moments, helping to reconstruct the conditions that prevailed just after the Big Bang and shedding light on the fundamental mechanisms operating at the tiniest scales imaginable. In the timeline of the universe's birth and evolution, gravity holds a special place. It is believed to have split off from the other fundamental forces extremely early, likely before what physicists call the Grand Unification epoch, a period when the remaining three forces, namely the strong nuclear force, weak nuclear force, and electromagnetism, were still merged into one unified force. The exact moment when gravity separated remains uncertain, but theoretical models suggest it happened incredibly fast, within the first 10 to the power of minus 32 seconds after the Big Bang. At these unimaginably high energy levels, the differences between the forces were blurred due to the extreme conditions. As the universe expanded and its temperature dropped, gravity distinguished itself from the unified force, while the other three forces stayed combined for a while longer. Scientists propose that gravity is fundamentally unique because it is not just a force but a geometric phenomenon. According to Einstein's general theory of relativity, gravity arises from the curvature of space-time caused by mass and energy, rather than being mediated by force-carrying particles like electromagnetism or the nuclear forces. This geometric nature gives gravity its distinct role in shaping the cosmos. The separation of gravity likely predated the splitting of the electroweak force into its electromagnetic and weak components, making gravity the first fundamental force to emerge independently from the primordial energy soup. This precedence grants gravity a dominant role in the large-scale structure of the universe, governing how galaxies, stars, and planets form and move within the vast cosmic web. Yet, the story of gravity's origins remains one of the greatest puzzles in physics. Understanding when and how gravity parted ways from the other forces continues to challenge researchers, inspiring ongoing exploration in theoretical physics and cosmology. These investigations are crucial not only for mapping the universe's birth, but also for potentially unifying gravity with the other forces through a quantum theory of gravity, a holy grail in modern science. Turning to the strong nuclear force, often simply called the strong force, it is the mightiest of the four fundamental forces, though it operates only over incredibly tiny distances, less than 1 femtometer, which is about 100,000 times smaller than the width of an average atom. This force acts as the glue that binds protons and neutrons together inside atomic nuclei, overcoming the electromagnetic repulsion between the positively charged protons that would otherwise push them apart. The strong force arises from interactions involving gluons, the massless particles that act as force carriers for this interaction. Gluons bind quarks, the elementary constituents of protons and neutrons, by constantly exchanging between them, creating a powerful binding energy. This energy is so intense that it accounts for most of the mass of atomic nuclei, thanks to the principle of mass-energy equivalence famously captured by Einstein's equation E=mc². The strong nuclear force came into being during the early universe's grand unification epoch, a transformative phase when the cosmos cooled enough for the initially combined forces to start differentiating. It separated from the electroweak force as the universe reached certain energy thresholds, undergoing a series of symmetry breakings, moments when the uniform laws of physics began to distinguish different forces. In the infant universe, quarks and gluons floated freely within an extremely hot and dense quark-gluon plasma. As the universe expanded and cooled further, these quarks combined to form protons and neutrons, which then clumped together to form atomic nuclei. This phase transition cemented the strong nuclear force as the architect of atomic nuclei, ensuring their stability despite the electromagnetic forces trying to push protons apart. Beyond holding nuclei together, the strong force is fundamental to the processes inside stars. It powers nuclear fusion, where hydrogen nuclei collide and fuse to form helium, releasing vast amounts of energy that light up the cosmos. This process sustains stars like our Sun and drives the cosmic engines that shape galaxies and planetary systems. The concept of symmetry breaking is central to understanding how the universe evolved from a hot, undifferentiated state into the complex cosmos we observe today. In physics, symmetry refers to a system's invariance under certain transformations, like how a perfect sphere looks identical no matter how it is rotated. Early in the universe's history, the laws governing particles and forces exhibited perfect symmetry, meaning the fundamental forces were indistinguishable from one another. As the universe cooled, these symmetrical states broke down, allowing forces to differentiate and particles to acquire mass, leading to the rich variety of matter and energy we see. These symmetry breakings are not just abstract ideas. They represent real transitions that shape the universe's physical laws and set the stage for the formation of atoms, stars, and galaxies. In exploring these fundamental forces, their origins, and their interactions, physicists are not just unraveling the story of the cosmos's birth, but are also moving toward a deeper understanding of the universe's very essence, its structure, behavior, and ultimate fate. However, as the universe expanded and gradually cooled, a remarkable transformation took place. A series of fundamental symmetries began to shatter, giving rise to the distinct forces and particles that shape everything around us today. One of the most pivotal moments in this cosmic evolution was the event known as electroweak symmetry breaking. In the blazing furnace of the early universe, at unimaginably high energy levels, the electromagnetic force and the weak nuclear force were not separate entities, but merged into a single unified force called the electroweak force. This unity represented a perfect symmetry in nature. As the universe's temperature dropped to a critical point, this delicate balance could no longer be sustained. The symmetry broke, causing the electroweak force to split into two distinct forces: the familiar electromagnetic force, responsible for light and electricity, and the weak nuclear force, which governs radioactive decay and nuclear processes within stars. This breaking of symmetry was essential. It allowed the weak nuclear force to behave differently, enabling vital processes that lead to the synthesis of elements and the energy production fueling stars throughout the cosmos. Another key chapter in this unfolding story occurred during what physicists call the Grand Unification epoch. As the universe continued its steady cooling, the strong nuclear force, the force that binds quarks together inside protons and neutrons, emerged as a separate force from the electroweak force through yet another profound symmetry breaking. This division was crucial because the strong force's distinct identity allowed the formation of atomic nuclei, the dense cores at the heart of atoms. Without this step, the universe could not build the complex matter that forms everything from the smallest grain of sand to the largest galaxy. But the saga of symmetry breaking did not end there. Theoretical frameworks like supersymmetry propose even deeper layers of symmetry that might have been broken in the early universe. Such breakings could unlock mysteries surrounding dark matter, an invisible substance that makes up most of the universe's mass but remains elusive to direct detection. These events hint at layers of complexity beyond our current understanding, suggesting the universe's evolution is richer and more intricate than once imagined. One of the most fascinating outcomes of symmetry breaking involves how fundamental particles gained mass. This phenomenon is explained through their interaction with the Higgs field, an invisible scalar field permeating all of space. The Higgs boson, discovered in 2012 at the Large Hadron Collider, is the particle associated with this field, and was a milestone in confirming the mechanism that endows particles with mass. Imagine the Higgs field as a cosmic molasses filling the universe. As particles move through it, they experience a kind of resistance that manifests as mass. In the immediate aftermath of the Big Bang, the universe was a seething, dense, and hot environment where all fundamental forces were united. As the universe cooled, symmetry breaking occurred in stages, leading to the differentiation of forces and allowing particles to acquire mass. This transition was a turning point. Before electroweak symmetry breaking, particles like the W and Z bosons, carriers of the weak nuclear force, were massless and capable of interacting over infinite ranges. Afterward, these particles gained mass through their interaction with the Higgs field, limiting the weak force to its observed short-range behavior. This shift was vital, shaping the interactions that underpin the formation of atoms, molecules, and ultimately the complex structures that populate the cosmos. Understanding these epochs of symmetry breaking provides an essential framework for grasping how the early universe transformed from a simple, uniform state of energy into a richly structured cosmos filled with particles, forces, and the building blocks of matter. It reveals the hidden mechanisms that orchestrated the universe's journey from chaos to complexity, highlighting the fundamental processes that have shaped every atom in our bodies and every star in the sky. This narrative stands as one of the most profound chapters in the story of cosmic evolution. The Higgs boson, often dubbed the God particle, holds a central place in our quest to understand the very fabric of the universe. This elusive particle is not just a scientific curiosity, it is the key to unlocking the mystery of mass itself. Without the Higgs field, an invisible energy field that permeates all of space, fundamental particles would remain weightless, forever drifting without the ability to form the matter we recognize. Imagine a universe where atoms could never take shape, where molecules failed to assemble, and where stars, planets, and life could never come into existence. The discovery of the Higgs boson confirmed this extraordinary mechanism, offering profound insight into how the universe evolved from an almost featureless expanse of energy into the richly structured cosmos we observe today. Rewind to the earliest moments after the Big Bang, when the universe was an unimaginably hot and dense cauldron of fundamental particles and intense energy. Among these building blocks were quarks, the elementary particles that would eventually forge the protons and neutrons at the heart of atoms. In this primordial epoch, quarks existed not as components trapped inside particles, but freely in a seething quark-gluon plasma, a dense, chaotic soup of energy where particles collided and interacted under the influence of the strong nuclear force. Gluons, the force carriers that mediate the strong nuclear force, played the role of cosmic glue, binding quarks together with immense power. But the behavior of quarks in this early plasma was unlike anything seen in the stable atoms we know today. The universe was expanding and cooling rapidly. Once the temperature dropped to roughly 100 billion degrees, quarks began to combine in a process called hadronization. This transformation gave birth to protons and neutrons, the baryons that would form the atomic nuclei. As cooling continued, a critical phase known as baryogenesis unfolded, allowing these particles to cluster and eventually form atomic nuclei. Then, about 380,000 years after the Big Bang, the universe reached a temperature low enough for electrons to attach to these nuclei, creating neutral atoms. This era, called recombination, was monumental. It ended the opaque, glowing plasma and ushered in a transparent universe filled with the first hydrogen and helium atoms. The release of photons at this time created the cosmic microwave background radiation, a faint afterglow still detectable today, and a cosmic fingerprint of the early universe. Quark's journey from free particles in a plasma to fundamental constituents of matter reveals the intricate dance of forces shaping our cosmos. They are the essential ingredients behind the formation of stars, galaxies, and ultimately life itself. Their transformation demonstrates the powerful interplay of fundamental particles and forces, a story that traces the universe's evolution from chaos to complexity. Within minutes of the Big Bang, another vital process unfolded: nucleosynthesis. During this brief but intense period, protons and neutrons fused to form the universe's first light elements. Hydrogen, consisting of a single proton, emerged as the most abundant element, accompanied by helium, composed of 2 protons and 2 neutrons. Trace amounts of lithium also appeared. These reactions, governed by the strong nuclear force under extreme conditions, vastly different from those today, produced about 75% hydrogen and 25% helium, setting the elemental foundation of the cosmos. As the universe expanded and cooled further, electrons combined with these nuclei to form neutral atoms, marking the end of recombination. This transition from a hot plasma to primordial gas allowed photons to travel unhindered, illuminating the universe for the first time. The resulting cosmic microwave background radiation offers a snapshot of this moment, a relic radiation that has traveled across billions of years to reach us. These first atoms were the building blocks for the grand cosmic structures that followed. Over billions of years, gravity caused clouds of primordial gas to collapse, giving rise to stars, galaxies, and eventually the complex tapestry of elements and life that fills the universe. From the smallest quarks to the vast galaxies, the story of our cosmos is a testament to the profound connections between fundamental particles and the forces governing them, a narrative of creation, transformation, and endless discovery. The quark-gluon plasma is an extraordinary and rare state of matter, a fleeting but crucial phase that existed mere moments after the birth of the universe itself. In this primordial era, the cosmos was unimaginably hot and dense, so intense that the familiar building blocks of matter, protons and neutrons, could not hold together in their usual form. Instead, their fundamental constituents, quarks and gluons, were liberated, roaming freely in an ultra-hot, super dense soup that defied the normal rules of particle physics as we know them today. This remarkable phase is believed to have lasted only about 1 microsecond, just a millionth of a second, following the Big Bang, when temperatures soared into the trillions of degrees Celsius. Under these extreme conditions, the quarks and gluons existed independently, no longer confined within the particles that typically bind them together. This was a world radically different from the one we experience. The forces that usually lock quarks inside protons and neutrons were overcome by the staggering heat and energy of the early universe. Since those fleeting moments, the universe has cooled dramatically, allowing quarks and gluons to recombine and form stable particles, setting the stage for atoms, stars, galaxies, and ultimately life itself. Yet replicating the quark-gluon plasma on Earth has proven a scientific challenge, one met only recently through cutting-edge experiments. Using powerful particle accelerators like the Large Hadron Collider in Europe and the Relativistic Heavy Ion Collider in the United States, scientists smashed together heavy atomic nuclei at nearly the speed of light. In these high-energy collisions, for just an instant, conditions mimic those of the early universe, freeing quarks and gluons once again from their usual confines. The insights gained from these experiments are invaluable. They allow physicists to probe the fundamental behavior of matter under extreme conditions and to better understand the forces that governed the universe's infancy. The discovery and study of the quark-gluon plasma illuminate a critical chapter in cosmic history, revealing how the universe transitioned from an unstructured, searing hot plasma to the rich, complex matter that makes up the cosmos today. Closely related to this early universe story is the puzzle of baryogenesis, the theoretical process that seeks to explain why the universe is dominated by matter rather than antimatter. During the Big Bang, matter and antimatter particles were created in roughly equal amounts, yet the observable universe is overwhelmingly composed of matter. This discrepancy raises one of the most profound questions in cosmology. Why does matter prevail? Baryogenesis offers possible answers. It suggests that certain physical processes in the early universe favored the production of baryons, particles like protons and neutrons, over their antimatter counterparts. Central to this idea is the violation of baryon number symmetry, a subtle but crucial imbalance in particle interactions. During the rapid expansion and cooling after the Big Bang, conditions may have existed that allowed more baryons to be created than antibaryons, breaking the expected symmetry between matter and antimatter. Several theoretical models explore this imbalance, including scenarios involving phase transitions in the electroweak force, the fundamental interaction that unites electromagnetic and weak nuclear forces. These models propose mechanisms where particle interactions fail to produce equal numbers of baryons and antibaryons, tipping the scales in favor of matter. Understanding baryogenesis is not only essential to explaining the universe's matter composition, but also to unraveling deeper mysteries of particle physics and the unification of forces. If matter and antimatter had been created in perfect symmetry, they would have annihilated each other completely, leaving behind a universe devoid of stars, planets, and life. The existence of baryogenesis helps explain why the cosmos is filled with matter, shaping the galaxies, stars, and planets that we observe today. It remains a top priority for physicists and cosmologists, promising to reveal new physics beyond current models and deepen our grasp of the universe's earliest moments and evolution. Among the many elusive particles that shed light on the early universe are neutrinos, tiny, nearly massless particles that interact so weakly with matter that billions of them pass through your body every second without leaving a trace. Their ghostly nature allows neutrinos to act as cosmic messengers, carrying information from the universe's first seconds after the Big Bang. Neutrinos decoupled from other matter during a period known as neutrino decoupling, occurring when the universe cooled enough to let them travel freely through space. These primordial neutrinos are relics from the universe's infancy, offering a glimpse into conditions from a time otherwise inaccessible to direct observation. As researchers study neutrinos from cosmic sources, including the explosions of massive stars called supernovae and cosmic ray interactions, they piece together vital clues about the universe's temperature, density, and evolution. Detecting neutrinos requires extraordinary efforts, involving vast underground laboratories like Japan's Super Kamiokande and the Ice Cube Neutrino Observatory buried deep in the Antarctic ice. These detectors capture faint signals produced when neutrinos interact very rarely with matter, allowing scientists to analyze their properties and origins. Through neutrino research, we gain deeper insights into fundamental physics, including the behavior of particles and forces at play in the early universe. Studying neutrinos not only enriches our understanding of cosmic history, but also contributes to unraveling the mysteries of dark matter and the formation of galaxies. Their subtle messages help construct a complex but fascinating narrative of how the cosmos transformed from a hot, dense primordial state into the vast, structured universe we inhabit today. Underpinning much of our modern cosmological understanding is the Lambda cold dark matter model, or Lambda CDM for short. This framework provides the most successful description of the large-scale structure and evolution of the universe. In this model, Lambda represents the cosmological constant, a mysterious form of energy permeating all of space that drives the accelerating expansion of the universe, a discovery that revolutionized cosmology in recent decades. The cold dark matter component refers to matter that neither emits nor absorbs light, making it invisible to telescopes and other traditional means of observation. Despite being unseen, cold dark matter exerts gravitational influence, playing a vital role in the formation and clustering of galaxies and the cosmic web. Together, lambda and cold dark matter form the backbone of the standard model of cosmology, explaining how the universe has grown and evolved from its earliest moments to the vast expanse we observe today. This elegant model continues to be tested and refined as astronomers gather more precise data, yet many mysteries remain. The nature of dark energy, the exact properties of dark matter, and how these unseen components interact with ordinary matter are among the greatest questions driving contemporary research. Through the combined efforts of particle physics, astrophysics, and cosmology, we steadily move closer to unraveling the full story of the universe, from its explosive beginnings to its ongoing expansion into the unknown. However, the influence of this enigmatic substance extends far beyond mere gravitational pull. It plays an indispensable role in sculpting the very architecture of the cosmos. This comprehensive framework, known as the Lambda Cold Dark Matter Model, or Lambda CDM, emerges from a remarkable synthesis of observations spanning multiple realms of astrophysics. It weaves together the faint whispers of the cosmic microwave background radiation, the sprawling distribution of galaxies across the universe, and detailed surveys of exploding stars called supernovae, forming an intricate tapestry that portrays the birth and evolution of the universe over billions of years. At its core, the Lambda CDM model seamlessly integrates two cornerstone theories of modern science: the Big Bang theory, which describes the universe's explosive origin from an unimaginably hot and dense state, and Einstein's general relativity, which governs the laws of gravity and space-time. This union offers an elegant and coherent picture of cosmic history, explaining not only how the universe began, but also how it has grown and changed through epochs of cosmic time. One of the most astonishing revelations from this model is the prediction and inclusion of a mysterious component known as dark energy. Dark energy constitutes approximately 70% of the total energy content of the universe, yet it behaves in ways that defy conventional understanding. Instead of pulling matter together through gravity, dark energy appears to exert a repulsive force that counterbalances gravitational attraction, causing the expansion of the universe to accelerate rather than slow down. This discovery, which overturned decades of assumptions, was first suggested in the late 20th century by observations of distant supernovae, revealing that galaxies are moving away from each other at an ever-increasing pace. Complementing dark energy is cold dark matter, which accounts for roughly 25% of the universe's total mass energy composition. Unlike ordinary matter, which interacts with light and other electromagnetic forces, cold dark matter interacts primarily through gravity, silently orchestrating the large-scale structure of the cosmos. It acts as a cosmic scaffold around which galaxies cluster and evolve. In the early universe, shortly after the Big Bang, dark matter began to clump under its own gravitational pull, forming dense regions that attracted ordinary matter, atoms, gas, and dust, allowing the first stars and galaxies to ignite. The Lambda CDM model excels at explaining a wide range of observational phenomena. For instance, it accounts for the extraordinary uniformity observed in the cosmic microwave background radiation, the afterglow of the Big Bang, and describes the vast web-like distribution of galaxies across space. Yet, despite its successes, this model does not answer all cosmic questions. The fundamental nature of dark matter and dark energy remains one of the greatest enigmas in contemporary physics, driving a relentless pursuit among scientists to understand what these invisible components truly are. Dark energy, in particular, has transformed our understanding of cosmic destiny. While early cosmological models predicted that gravity would gradually slow the universe's expansion, possibly culminating in a stable or collapsing cosmos, the accelerating expansion implies a vastly different future. Instead of collapsing back on itself, the universe may continue expanding forever, with galaxies drifting ever farther apart in an increasingly cold and empty space. This realization has forced scientists to rethink the forces shaping cosmic evolution, suggesting a complex interplay between gravity and dark energy that will define the universe's fate for eons to come. Meanwhile, dark matter remains a silent yet powerful architect of cosmic structure. Though it neither emits nor absorbs light, its gravitational fingerprint is unmistakable in the motion of stars, the bending of light around massive objects, and the clustering patterns of galaxies. Without dark matter's invisible hand, ordinary matter alone could not have formed the intricate cosmic web we observe today. Gas clouds would have struggled to collapse and ignite the first stars, and the universe's majestic tapestry of galaxies and clusters would be vastly diminished. Together, dark matter and dark energy reveal a universe far more mysterious and dynamic than once imagined. The Lambda CDM model offers a profound lens through which we glimpse the cosmos, one that tells a story of explosive beginnings, accelerating expansion, and the silent forces shaping all that we see and much more that remains hidden. As scientists continue their quest to uncover the true essence of these dark components, the universe stands as a vast frontier of mysteries, inviting exploration and inspiring wonder about our place within this grand cosmic journey. Furthermore, dark matter plays a crucial role in shaping the intricate dynamics of galaxies, influencing their very motion and stability in ways that visible matter alone cannot explain. Observations have revealed a puzzling phenomenon. Stars within galaxies travel at speeds far greater than what the mass of the stars and gas we can see would allow. This unexpected velocity hints at the presence of an invisible mass, dark matter, that envelops galaxies in vast, unseen halos. These halos act as cosmic anchors, stabilizing galaxies against the centrifugal forces that would otherwise tear them apart and fundamentally altering their rotation patterns and overall behavior. But the influence of dark matter extends far beyond individual galaxies. Within massive galaxy clusters, dark matter's gravitational pull dominates the landscape, guiding the assembly and interaction of countless galaxies. On a grander scale, it sculpts the large-scale structure of the universe itself. Dark matter forms the backbone of an immense cosmic network, a vast web of filaments and clusters stretching across billions of light years. Gravity, acting predominantly on dark matter, molds this cosmic architecture, dictating how galaxies group together, collide, and evolve over billions of years. Unlocking the mysteries of dark matter has become a central pursuit in cosmology, offering crucial insights into the universe's history. It bridges the enigmatic gap between the Big Bang, the explosive origin of everything, and the magnificent tapestry of galaxies we observe in the cosmos today. Through relentless research and observation, scientists continue to unravel dark matter's elusive nature, gradually illuminating fundamental questions about the formation and evolution of the universe itself. One of the most fascinating manifestations of this grand cosmic order is the cosmic web, an enormous and complex structure that reveals how matter is distributed on the largest scales. Composed primarily of dark matter, interwoven with galaxies, this web consists of long filaments that stretch across mind-boggling distances, connecting clusters of galaxies like a vast spider's web spun across the cosmos. This interconnected structure is fundamental to understanding how galaxies and galaxy clusters are arranged in space, providing a framework for the universe's large-scale organization. The formation of the cosmic web began shortly after the Big Bang, during an epoch when the universe was extremely hot and dense. At first, matter was almost evenly spread throughout space, but tiny quantum fluctuations, minuscule variations in density during a rapid expansion phase known as inflation, created slight irregularities. Over time, these tiny differences grew under the influence of gravity, particularly from dark matter, which began to collapse into dense regions. These dense clumps of dark matter acted as gravitational wells, pulling in ordinary matter and giving rise to the filamentary network that defines the cosmic web today. As the universe continued to expand and cool, the cosmic web evolved further. Dark matter, unaffected by electromagnetic forces and invisible to telescopes, remained the dominant force shaping the web. The densest concentrations of dark matter formed the nodes of the web, where galaxies and galaxy clusters congregated, creating some of the richest and most massive structures in the universe. This gravitational scaffolding guided the flow of ordinary matter, gas, dust, and eventually stars, enabling the formation of galaxies along the filaments. Over billions of years, this dynamic interplay between dark matter and visible matter crafted the complex cosmic landscape we observe through powerful telescopes. Thanks to advanced astronomical surveys and deep observations of distant galaxies, scientists have been able to map the cosmic web in remarkable detail. The patterns of clustering and connectivity among galaxies within these filaments reveal key insights into how cosmic structures grow and evolve. This knowledge helps cosmologists piece together the grand-scale dynamics of the universe, providing a roadmap for understanding how galaxies form, change, and interact throughout cosmic history. Computer simulations stand at the forefront of these discoveries, serving as vital tools to recreate and study the early universe's intricate processes. These simulations incorporate fundamental physical laws, including gravity, electromagnetism, and thermodynamics, to model complex phenomena that are impossible to replicate in laboratory experiments. By inputting known properties of the universe, scientists simulate the evolution of matter, energy, and light, from the fiery moments following the Big Bang to the present day. A crucial strength of these simulations lies in their ability to reproduce the extreme conditions of the early universe, such as the intense temperatures and densities that prevailed during the universe's infancy. They track critical phases like particle formation, nucleosynthesis, the creation of atomic nuclei, and the assembly of the first cosmic structures. By following the interactions between dark matter, baryonic ordinary matter, and radiation, these models offer a comprehensive picture of the cosmic dawn and the forces that shape the cosmos into what we see now. Through these detailed studies, humanity moves closer to uncovering the true nature of dark matter and its profound impact on the universe's evolution. Each new discovery reveals another thread in the cosmic web, helping us understand not only where we come from, but also the fundamental forces that govern the vast, mysterious expanse beyond our world. Furthermore, computer simulations have revolutionized the way scientists investigate the origins and evolution of the universe. By tweaking initial parameters such as the density of dark matter or the universe's expansion rate, researchers can recreate a variety of cosmic scenarios within these virtual laboratories. This capability allows them to test and compare different cosmological models, examining how closely each aligns with the wealth of observational data collected from telescopes and satellites. This iterative process, constantly refining simulations and matching them against real-world evidence, serves as a powerful method to deepen our grasp of fundamental cosmic phenomena, including the rapid inflationary expansion after the Big Bang, the mysterious era of baryogenesis when matter gained dominance, and the vast cosmic web that connects galaxies through filaments of dark matter and gas. Over time, these simulations have validated key predictions of the prevailing lambda cold dark matter, Lambda CDM model, confirming its robustness in explaining the universe's accelerating expansion and large-scale structure. Beyond merely affirming existing theories, simulations have uncovered unexpected phenomena, providing fresh clues about the hidden dynamics of cosmic evolution. This collaboration between cosmologists and computational scientists continuously pushes the boundaries of our knowledge, making advanced simulations indispensable in modern cosmology. These digital experiments not only illuminate the universe's earliest moments, but also inform the design of future astronomical observations and experiments, gradually painting a more complete and nuanced picture of the cosmos. One particularly fascinating theoretical concept emerging from such studies is the idea of cosmic strings, hypothetical, ultra-thin, one-dimensional defects in space-time that could have formed during phase transitions in the early universe. According to certain mathematical frameworks in fundamental physics, these cosmic strings are relics left behind when the universe underwent symmetry breaking as it cooled from its initial unimaginably hot state. To understand this, imagine a stretched rubber band, full of tension along its length. Cosmic strings are thought to concentrate enormous amounts of energy along their slender forms, potentially influencing the universe's large-scale structure and behavior. If cosmic strings truly exist, they wouldn't shine or glow like stars, making them invisible in conventional ways. However, their immense gravitational pull could bend the path of light traveling near them, a phenomenon known as gravitational lensing. This effect might distort or multiply the images of distant celestial objects, offering a possible indirect method of detecting these elusive structures. Cosmic strings are believed to have formed during periods of rapid expansion, such as the Inflationary epoch, and may have played a role in pulling matter together, helping to seed the formation of galaxies and clusters. Although cosmic strings remain theoretical with no direct observations yet, their study remains a vital frontier in cosmology. Confirming their existence would shed light on the physics of the universe's earliest moments, the nature of cosmic inflation, and the fundamental forces shaping reality. The search for cosmic strings is part of the broader human quest to unravel the universe's complex tapestry and the underlying principles governing it. Different cosmological models shape how scientists understand the Big Bang, offering various lenses through which to interpret the universe's birth and growth. Each model carries its own assumptions about the universe's makeup, its rate of expansion, and the fundamental forces involved. Exploring these frameworks enables researchers to gain deeper insights into not only how the universe began, but also how it has changed over time and what its ultimate fate might be. The most widely accepted framework today is the Lambda CDM model, which combines the cosmological constant, a form of dark energy causing the universe's accelerated expansion, with cold dark matter, an invisible substance that helps pull matter together through gravity. This model successfully explains a broad range of observations, from the cosmic microwave background radiation, relic light from the Big Bang, to the distribution of galaxies across space. It portrays the Big Bang not as a single explosive event, but as the start of continuous expansion, shaped by dark energy and dark matter, revealing the profound complexity behind the universe's evolution. In contrast, alternative theories offer radically different views. The Cyclic model suggests the universe undergoes endless cycles of expansion and contraction, implying that the Big Bang is just one of many such cosmic rebirths. This idea challenges the traditional linear timeline of cosmic history, raising profound questions about what existed before the Big Bang and whether past universes influence the present one. Another innovative concept is the ekpyrotic model, which imagines our universe emerging from the collision of two three-dimensional branes in a higher dimensional space. Rather than the Big Bang being the absolute beginning, this scenario views it as a transformative event resulting from a complex interaction in dimensions beyond our everyday experience. Each of these cosmological models contributes uniquely to the ongoing dialogue in astrophysics. By exploring their distinct physics and observational predictions, scientists can refine their understanding of cosmic origins. Comparing these theories helps direct future research and shape the questions asked of new data, bringing humanity closer to uncovering the fundamental rules that govern the cosmos. Supporting this quest are galaxy surveys, which systematically map and catalog millions of galaxies across vast stretches of the sky. These surveys are critical because they provide detailed snapshots of the universe's large-scale structure, revealing how galaxies formed, clustered, and evolved over billions of years since the Big Bang. Through this cosmic census, astronomers can trace the universe's history, test cosmological theories, and improve models that describe the vast, ever-changing cosmic landscape. One of the most groundbreaking achievements of galaxy surveys lies in their remarkable ability to map out the large-scale distribution and density of galaxies across the vast cosmos. Contrary to the simple idea that galaxies float randomly through space, these surveys reveal a stunningly intricate network known as the cosmic web, a sprawling web-like structure composed of filaments, clusters, and voids. This cosmic architecture offers profound clues about the unseen forces shaping our universe. In particular, it provides compelling evidence for the presence and gravitational influence of dark matter, an invisible substance that formed soon after the Big Bang and continues to mold the universe's structure today. This vast cosmic web also reflects the dynamic effects of cosmic expansion, highlighting how the universe's growth has influenced where and how galaxies form. By studying this large-scale structure, scientists can peer back into the universe's infancy. The distribution patterns of galaxies allow researchers to reconstruct the forces and events that unfolded shortly after the Big Bang, testing and refining leading cosmological models like the Lambda Cold Dark Matter, Lambda CDM framework. This model combines dark matter, dark energy, and ordinary matter to explain the universe's evolution and galaxy surveys provide the critical data needed to validate its predictions. Beyond mapping, galaxy surveys serve as a powerful tool for tracking the evolution of galaxies through time. Using a technique called redshift measurement, astronomers can detect how light from distant galaxies stretches as the universe expands, effectively allowing us to see galaxies as they appeared at different points in cosmic history. Redshift acts as a cosmic time machine, showing us galaxies from billions of years ago and enabling scientists to piece together the narrative of galaxy formation and transformation over epochs. This timeline helps test theoretical ideas about how the universe's initial conditions led to the rich diversity of galaxies observed today. Galaxy surveys also shed light on how galaxies cluster and grow, observing the formation of galaxy groups and massive clusters. The properties of these clusters, their size, mass, and distribution, impose tight constraints on cosmological parameters and provide insight into the nature of mysterious phenomena such as dark energy and dark matter. These findings reinforce the picture of an expanding universe that began as a hot, dense state in the Big Bang, linking current observations with the earliest moments of cosmic history. Serving as a cornerstone for modern cosmology, galaxy surveys connect the present-day universe to its primordial origins. They offer empirical evidence that helps scientists verify theoretical models of the Big Bang, clarify the influence of dark matter and dark energy, and unravel the complex cosmic processes shaping the universe over billions of years. Among the most valuable treasures in this cosmic tapestry are the oldest galaxies ever observed. These ancient stellar cities formed just a few 100 million years after the universe's birth, providing a rare window into the conditions of the primordial cosmos. By studying these early galaxies, their mass, composition, and rates of star formation, astronomers gain critical insights into the universe's formative stages. They reveal not only how galaxies began, but also the elemental ingredients present during those first moments. Light emitted from these distant galaxies carries spectral fingerprints, showing scientists the elemental makeup of the early universe. This helps unravel the processes of nucleosynthesis, the cosmic forge where the first atomic nuclei formed shortly after the Big Bang. Furthermore, these observations shed light on the first generation of stars, which played a pivotal role in enriching the interstellar medium with heavier elements through explosive supernova events. The chemical evolution of the cosmos, tracked through these ancient galaxies, is essential to understanding how complex structures, including planets and ultimately life, came to exist. Comparing these early galaxies to those in the modern universe reveals striking differences. Early galaxies often appear smaller, irregular, and less orderly, hinting at a turbulent youth marked by frequent mergers and interactions. Over cosmic time, these processes shaped the galaxies into the majestic spirals and ellipticals we see today. This evolutionary tale, pieced together from observations of galaxies across time, illustrates the dynamic and interconnected nature of cosmic development. Moreover, the light from the oldest galaxies allows astronomers to measure how fast the universe expanded at various stages. By carefully determining their distances and redshifts, scientists can fine-tune cosmological models and better understand the elusive force known as dark energy, which drives the accelerated expansion of the universe. In essence, these ancient galaxies act as time capsules, unlocking secrets of the universe's earliest epochs and deepening our understanding of fundamental cosmic phenomena. They bridge the gap between theoretical predictions and direct observations, illuminating the journey from a simple hot gas to the vast, structured universe we inhabit today. Among the brightest and most powerful lighthouses of the early universe are quasars, extraordinary celestial objects fueled by supermassive black holes at the hearts of galaxies. As these black holes voraciously consume surrounding material, the infalling gas heats to incredible temperatures, emitting intense electromagnetic radiation that makes quasars visible across unimaginable distances. Because quasars are found at the farthest reaches of the cosmos, observing them allows scientists to peer back billions of years, effectively watching the universe in its youth. One of their most crucial contributions is illuminating the otherwise invisible intergalactic medium, the vast stretches of gas and dust between galaxies. As quasar light travels through space, it interacts with this diffuse matter, creating distinctive absorption features in their spectra. By studying these absorption lines, astronomers gain vital information about the composition, density, and temperature of the intergalactic gas at different points in cosmic history. This window into the past sheds light on the epoch of reionization, a pivotal era when the first stars and galaxies ignited and began ionizing the hydrogen gas filling the universe, transforming it from opaque to transparent. Through the combined power of galaxy surveys and quasar observations, we continue to unravel the universe's grand story, from its explosive beginnings through the formation of the first stars and galaxies to the complex cosmic web that binds everything together today. Additionally, the redshift observed in quasars provides astronomers with crucial insights into the expansion of the universe. As these incredibly distant and powerful objects emit light, that light is stretched to longer wavelengths during its journey to us, a direct consequence of the universe itself expanding. This stretching of light, known as the Doppler effect, shifts the observed light toward the red end of the spectrum, hence the term redshift. By carefully measuring the redshift of quasar light, scientists can determine how far away these celestial beacons are. This, in turn, allows them to infer the rate at which the universe is expanding at different periods in its vast history. Such measurements refine cosmological models, giving us a clearer picture of the forces driving cosmic evolution. Quasars are not just distant markers. They serve as powerful tools to study the formation and growth of supermassive black holes. Observing quasars at varying redshifts reveals how rapidly these enormous black holes emerged in the early universe and how they evolved over billions of years. By understanding the connection between quasar activity and the birth of galaxies, researchers gain insight into the assembly of large-scale cosmic structures. Quasars illuminate the early universe, offering a window into the intergalactic medium, the sparse gas and dust filling the space between galaxies, and the dynamic interplay between black holes and galaxy formation. As astronomers delve deeper into quasar studies, their findings continue to enrich our comprehension of the cosmic story and the processes that shape the universe we observe today. Redshift itself is a fundamental astronomical phenomenon occurring when light emitted from distant objects like galaxies stretches toward longer wavelengths as those objects move away from us. This shift toward the red end of the light spectrum is most notably explained by the Doppler redshift, which happens because of the relative motion between the light source and the observer. In the context of an expanding universe, galaxies generally move away from each other, making their emitted light appear redshifted. The farther a galaxy is, the faster it seems to recede, resulting in a greater redshift. This direct relationship between redshift and distance was famously documented by Edwin Hubble in the early 20th century. His observations provided compelling evidence that the universe is expanding. Hubble's law, one of the cornerstones of modern cosmology, states that the velocity at which a galaxy moves away from us is directly proportional to its distance. This discovery not only linked redshift to cosmic expansion, but also paved the way for measuring the universe's growth over time. Through redshift analysis, scientists estimate distances to galaxies and calculate the speed of universal expansion. This has led to the understanding that the universe has been growing since the Big Bang, which occurred roughly 13.8 billion years ago. Moreover, redshift studies have played a pivotal role in revealing the mysterious acceleration of the universe's expansion. Observations of distant supernovae, stellar explosions acting as cosmic mileposts, showed that not only is the universe expanding, but this expansion is speeding up. This unexpected discovery gave rise to the concept of dark energy, an enigmatic force driving the acceleration. Redshift thus becomes an indispensable tool in cosmology, linking the motion of distant celestial objects to the fundamental dynamics shaping the universe's past, present, and future. In another revolutionary chapter of cosmic exploration, gravitational waves offer a fresh perspective on the universe's most cataclysmic events. First predicted by Albert Einstein over 100 years ago, gravitational waves are ripples in the very fabric of space-time itself. They are produced by some of the most violent cosmic collisions, such as those between black holes or neutron stars. Detecting these waves allows scientists to observe phenomena invisible through traditional means like light or radio waves. This is especially crucial for understanding conditions in the universe's infancy, mere fractions of a second after the Big Bang, when the cosmos was a hot, dense, and turbulent environment filled with rapid, energetic processes. As the early universe expanded and cooled, gravitational waves created during that era traveled unimpeded across the cosmos, carrying with them invaluable information about the universe's origins. Today, sophisticated instruments like LIGO and Virgo enable researchers to detect these faint signals from distant cosmic events. By analyzing the wave's characteristics, scientists can deduce the energy released, the distance of the events from Earth, and the nature of the sources that produced them. This new window into the universe continues to deepen our understanding of the cosmic past and reveals the dynamic processes shaping the universe on the grandest scales. Moreover, these gravitational waves open a window into realms of physics that remain unreachable by traditional light-based observations. In places so dense and extreme, like the cores of neutron stars, where light itself cannot escape, gravitational waves become our unique messenger. They provide an unprecedented opportunity for astronomers to probe the universe's earliest moments, including the elusive phase known as cosmic inflation. This brief but dramatic period involved an exponential expansion of space-time that likely occurred mere fractions of a second after the Big Bang, setting the stage for the cosmos we inhabit today. As the field of gravitational wave astronomy advances, it holds the promise of revealing even deeper secrets about the universe's infancy. Beyond shedding light on the nature of dark matter and dark energy, two of the greatest mysteries in modern physics, it offers fresh insights into the fundamental forces that govern reality. This emerging era of exploration adds a vital chapter to humanity's enduring quest to comprehend the cosmos and our place within it. The study of primordial elements, the first atoms forged in the aftermath of the Big Bang, further enriches this cosmic narrative. These elements, mainly hydrogen, helium, and tiny traces of lithium and beryllium, serve as crucial clues to understanding the conditions that prevailed during the universe's formative moments. By examining the abundance and distribution of these primordial building blocks, scientists peer through the veil of time to glimpse the environment that existed just minutes after the universe's explosive birth. Utilizing cutting-edge telescopes and highly sensitive detectors, researchers observe the ancient light of the cosmic microwave background. This faint relic radiation is a direct remnant of the searing hot, dense plasma that filled the universe shortly after the Big Bang. Through detailed analysis of this background glow, scientists can deduce the amounts of primordial elements produced during a process called nucleosynthesis, the formation of new atomic nuclei, which unfolded within the universe's first few minutes. This comparison between theoretical predictions and actual observations sharpens our cosmological models and deepens our understanding of particle physics. Even more, the relative distribution of these primordial elements unlocks secrets about how the early universe evolved. For example, the ratio of helium to hydrogen offers vital clues about the density of baryonic matter, the ordinary matter that composes stars, planets, and life itself. This density influences how quickly the universe expands. As primordial elements coalesce, they eventually give rise to the formation of stars and galaxies. Tracing this process illuminates the timeline of cosmic history and reveals the mechanisms behind the structure formation that shapes everything we see in the night sky. By studying these ancient elements, scientists unravel fundamental truths not only about the early universe, but also about stellar life cycles and the ongoing story of cosmic evolution. Each discovery acts as a piece of the ultimate cosmic puzzle, the origin and unfolding of the universe itself. Expanding our view to large-scale structures, the grand tapestry of galaxies and galaxy clusters that stretch across the cosmos, provides further evidence supporting the Big Bang theory. By mapping these colossal formations, astronomers witness the evolution of matter from the universe's fiery beginnings to the vast, complex structures we observe today. Central to this understanding is the idea that the universe started in an extremely hot, dense state and has been expanding ever since. Over billions of years, tiny fluctuations in matter density served as seeds for gravitational attraction, drawing gas and dust into stars, galaxies, and clusters. Observing these structures allows scientists to reconstruct the history of cosmic evolution. Among the most compelling pieces of evidence is the cosmic web, a sprawling network of filaments and voids created by the interplay of dark matter and ordinary matter. The distribution of galaxies into clusters and superclusters aligns strikingly with predictions derived from Big Bang-based simulations. These massive cosmic structures grew from initial density fluctuations, which correspond to the subtle temperature variations found in the cosmic microwave background radiation. Observations by satellites have confirmed this harmony between theory and reality, reinforcing the concept that the universe has experienced continuous expansion and structure formation since its inception. Moreover, the observed redshift of distant galaxies offers another powerful confirmation. As light travels through expanding space, its wavelength stretches, shifting toward the red end of the spectrum. By measuring this redshift and linking it to a galaxy's distance, astronomers chart the history of the universe's expansion. This expanding cosmic landscape is consistent with predictions made by the Big Bang framework, highlighting the dynamic growth of large-scale structures over cosmic time. Together, these lines of evidence weave a compelling and cohesive story. They affirm the Big Bang as the most robust and comprehensive explanation for the universe we inhabit, a universe born from a singular explosive event, growing and evolving into the magnificent cosmic web we continue to explore today. The Hubble Space Telescope has revolutionized humanity's grasp of the cosmos, serving as a window into the earliest moments of our universe and the processes that shaped it. Launched in the early 1990s, this remarkable observatory orbits Earth free from the distortion of our atmosphere, capturing breathtakingly detailed images and invaluable data across multiple wavelengths of light. These observations have enabled astronomers to peer far deeper into space and time than ever before, bringing to life the story of the universe's birth and its ongoing evolution. One of Hubble's most groundbreaking contributions has been its precise measurement of the universe's rate of expansion, known as the Hubble constant. By observing distant exploding stars called supernovae, as well as pulsating Cepheid variable stars whose brightness varies in predictable cycles, Hubble allowed scientists to calculate distances with extraordinary accuracy. This, in turn, enabled the determination of how fast the cosmos is stretching. Understanding this expansion rate is not just an abstract curiosity. It provides essential clues about the age of the universe and confirms that it originated from an extremely hot, dense state, roughly 13.5 billion years ago. This concept forms the cornerstone of the Big Bang theory. Beyond measuring expansion, Hubble has taken humanity on a journey back through time by observing galaxies whose light has traveled billions of years before reaching its instruments. These ancient galaxies, viewed as they appeared when the universe was still in its infancy, offer a direct glimpse into the earliest stages of cosmic structure formation. The telescope has revealed galaxies forming earlier than once believed, showing that the universe grew complex structures surprisingly quickly after the initial explosion. The discovery of galaxies at extremely high redshifts, a term that describes how much their light has been stretched by cosmic expansion, has reshaped our timeline for cosmic evolution, confirming theories about how matter coalesced into the vast web of galaxies we see today. Hubble has also contributed significantly to our understanding of the cosmic microwave background radiation, the faint afterglow left from the Big Bang. By combining its observations with those from missions like the Wilkinson Microwave Anisotropy Probe, scientists have mapped tiny temperature fluctuations in this radiation. These subtle irregularities correspond to the primordial seeds from which large-scale cosmic structures eventually grew, providing compelling evidence supporting Big Bang predictions. While Hubble transformed cosmology, the James Webb Space Telescope represents the next giant leap in astronomical exploration. Launched in late 2021, Webb is equipped with cutting-edge technology designed to observe the universe in infrared light, wavelengths longer than visible light that can penetrate cosmic dust clouds and unveil celestial objects hidden from optical telescopes. This ability is crucial for studying the universe's earliest galaxies and stars formed during a period known as the Cosmic Dawn, which occurred roughly between 500 million and 1 billion years after the Big Bang. Webb's mission is to illuminate this mysterious epoch, revealing not only when the first stars and galaxies appeared, but also how they evolved and ignited the process called reionization, which transformed the dark, opaque cosmos into the transparent, star-filled universe we inhabit today. Webb's powerful infrared instruments allow astronomers to analyze the chemical composition of these primordial galaxies, detecting elements and molecules that shed light on how the first stars formed and how heavier elements essential for life were synthesized. This knowledge helps answer profound questions about the universe's elemental origins and the processes that set the stage for planets, stars, and ultimately, life itself. Furthermore, Webb aims to unravel the mysteries of dark matter and dark energy, the enigmatic substances making up the majority of the universe's mass and energy, but remaining poorly understood. By mapping the distribution and behavior of galaxies in the early universe, Webb seeks to clarify how these invisible forces influenced cosmic evolution. Complementing these cosmic observatories, particle accelerators like the Large Hadron Collider have opened a new frontier in understanding the fundamental conditions present just moments after the Big Bang. Situated near Geneva, Switzerland, the Large Hadron Collider accelerates protons to nearly the speed of light before smashing them together in controlled high-energy collisions. These events recreate the extreme environments that existed fractions of a second after the universe's birth, allowing scientists to study fundamental particles and forces in unprecedented detail. Through these collisions, physicists explore phenomena such as the formation of quarks and gluons, the fundamental building blocks of protons and neutrons, giving insight into how matter itself formed. One of the most momentous discoveries from the Large Hadron Collider came in 2012 with the detection of the Higgs boson. This elusive particle, predicted decades earlier by the Standard Model of particle physics, is intimately linked to the origin of mass. The Higgs mechanism explains how particles acquire mass by interacting with the Higgs field permeating all space. This process was critical in shaping the early universe's evolution, influencing how matter clumped together to form the cosmos we observe today. Together, these marvels of technology, the Hubble Space Telescope, the James Webb Space Telescope, and the Large Hadron Collider, form a powerful alliance in humanity's quest to unravel the mysteries of the universe. They bridge the cosmic and the quantum, from the largest galactic structures to the tiniest particles, offering profound insights into our origins and the fundamental nature of reality itself. Through their discoveries, we continue to refine and expand the story of the cosmos, moving ever closer to answering some of the deepest questions about where we came from and what the universe truly is. Furthermore, particle accelerators stand as some of humanity's most powerful tools for probing the deepest mysteries of the cosmos, particularly those enigmas surrounding dark matter and the hidden forces shaping our universe. These colossal machines, like the Large Hadron Collider, do more than smash atoms at near-light speeds. They open windows into realms far beyond the familiar boundaries of the Standard Model of particle physics. By recreating conditions similar to those just fractions of a second after the Big Bang, scientists can search for new, exotic particles or previously unknown forces that might have existed in the universe's earliest moments. Each collision offers a rare glimpse into the building blocks of reality, potentially solving puzzles that have eluded physicists for decades and bridging the microscopic world of subatomic particles with the vast, expansive cosmos. Parallel to these efforts, the Sloan Digital Sky Survey, SDSS, serves as a monumental endeavor in mapping the universe with unprecedented scope and detail. Initiated in the early 2000s, the SDSS is more than just a telescope. It is a global collaboration dedicated to charting the night sky and cataloging millions of celestial objects. The treasure trove of data it produces is invaluable, giving astronomers a detailed map of the large-scale structure of the universe. By meticulously recording the positions and distances of galaxies, the survey reveals how these colossal islands of stars cluster and interact under gravity's influence, illuminating the unseen scaffolding of dark matter that holds them together. This cosmic census allows scientists to unravel the dynamic processes behind galaxy formation and evolution, and to better understand the mysterious dark energy that drives the accelerated expansion of the universe. What sets the Sloan Digital Sky Survey apart is its extensive use of spectroscopic techniques, studying the light emitted by stars, galaxies, and other celestial bodies to decode their chemical compositions, temperatures, and velocities. Such observations provide a window into the life cycles of stars and galaxies, helping track the universe's history through cosmic time. By analyzing light from distant supernovae and the cosmic microwave background radiation, the SDSS has refined cosmological models and lent critical support to the Big Bang theory. The survey's comprehensive open-access database has democratized astronomy, empowering both professional scientists and amateur enthusiasts worldwide to explore, analyze, and contribute to new discoveries. The flood of data has also spurred innovations in data science, with novel algorithms pushing the boundaries of what can be learned from the cosmos. Looking forward, the next generation of gravitational wave detectors promises to revolutionize our understanding of the universe's earliest epochs. Unlike light, gravitational waves, ripples in the fabric of spacetime caused by massive cosmic events, carry information from the most violent and distant corners of the cosmos. Future observatories, designed with far greater sensitivity and precision than today's instruments, will be able to capture these elusive signals from black hole collisions, neutron star mergers, and potentially from the universe's birth itself. Each detected wave acts as a cosmic messenger, offering unparalleled insights into extreme astrophysical environments and the fundamental forces governing matter and energy under unimaginable conditions. Perhaps most tantalizing is the prospect of detecting the primordial gravitational wave background, a faint, persistent hum generated during the universe's earliest moments, possibly during a period called cosmic inflation, when the universe expanded exponentially in a fraction of a second. Confirming and studying this signal would provide direct evidence of how the cosmos grew from a tiny, hot, and dense state into the vast expanse we see today. By unlocking the secrets encoded in these waves, scientists hope to uncover the energy scales and physical laws that shape the birth of everything, pushing the frontiers of cosmology into uncharted territory. Together, particle accelerators, sky surveys like the SDSS, and future gravitational wave detectors form a triumvirate of tools driving humanity's quest to understand the origins, structure, and destiny of the universe itself. Additionally, remarkable advancements in detector technology are opening new frontiers in the study of gravitational waves, allowing scientists to measure not only their presence but also their polarization. This added dimension of measurement reveals intricate details about the sources of these ripples in spacetime and the conditions under which they were formed. By analyzing the polarization patterns, researchers gain profound insights into the mechanisms behind cosmic events such as black hole mergers or neutron star collisions. More importantly, this data offers vital clues about the broader cosmological models that seek to explain the universe itself, shedding light on elusive phenomena like dark matter and dark energy, two of the most profound mysteries in modern astrophysics. The ability to probe gravitational waves with unprecedented precision will deepen our understanding of how various astrophysical processes interconnect, especially during the universe's earliest moments. This rich tapestry of information will help scientists trace the evolution of the cosmos from its chaotic beginnings to the structured expanse we observe today. Future gravitational wave observatories, equipped with cutting-edge technology, promise to unlock entirely new dimensions of knowledge about the universe's origins and the fundamental forces that govern it. These observatories could revolutionize how we comprehend gravity's role not just as a force, but as a storyteller of the cosmos's grand narrative. Parallel to these technological strides, advancements in computer modeling have drastically transformed our grasp of the Big Bang and the universe's subsequent evolution. As computational power has surged exponentially over the years, scientists have been empowered to develop increasingly sophisticated simulations that replicate a vast array of cosmic phenomena with extraordinary fidelity. These high-resolution models enable researchers to explore turbulent dynamics that shape the early universe, the birth and formation of galaxies, and the complex interplay of fundamental forces. By bridging the gap between theoretical physics and observational data, these simulations serve as virtual laboratories for testing hypotheses that would otherwise remain inaccessible. A particularly significant area of progress lies in simulating cosmic inflation, the dramatic and rapid expansion of the universe that took place mere fractions of a second after the Big Bang. Modern models now incorporate intricate physical processes, enabling scientists to investigate multiple inflationary scenarios and their far-reaching consequences. By carefully modeling how inflation influenced the distribution of matter and energy, researchers can trace the origins of the large-scale structures that eventually grew into the galaxies and clusters visible today. Moreover, these simulations predict distinct patterns in the cosmic microwave background radiation, the faint afterglow of the Big Bang, at which astronomers can then verify through meticulous observation. Beyond inflation, enhanced computational techniques have paved the way for detailed simulations of cosmic structure formation. These models integrate the effects of both ordinary matter and dark matter, unraveling how gravitational forces acted over billions of years to sculpt the cosmic web. By simulating the interactions, clustering, and evolution of particles, researchers gain invaluable insights into the processes that governed galaxy formation and growth, from initial density fluctuations in the primordial universe. This body of work has significantly refined our understanding of dark matter's critical role in shaping the cosmos, pushing the boundaries of what we know about the aftermath of the Big Bang. Furthermore, breakthroughs in numerical algorithms and parallel computing architectures now allow scientists to run large-scale simulations solving highly complex equations governing cosmological dynamics. These vast simulations capture an impressive range of cosmic phenomena, from the intricate cosmic web structure connecting galaxies to the behavior of high-energy particles accelerating through space. Not only do these models deepen our comprehension of the universe's birth and evolution, but they also strengthen the collaboration between theorists and experimentalists by providing testable predictions. These predictions are continually compared against real-world data collected by telescopes and detectors stationed around the globe, creating a dynamic feedback loop that drives cosmology forward. In the grand scheme, computer modeling has become an indispensable tool in modern cosmology, enabling scientists to explore the universe's fundamental properties with an unprecedented level of detail and accuracy. This synergy between observation and simulation is crucial for unlocking the mysteries of the cosmos. One of the central puzzles cosmologists face is the horizon problem, which emerges from observations of the cosmic microwave background radiation, the faint, almost uniform glow left over from the Big Bang. This radiation is astonishingly consistent across the sky, showing only minute temperature fluctuations. Yet, when considering the immense distances involved during the universe's infancy, this uniformity presents a profound challenge. Regions of space separated by vast distances appear nearly identical in temperature, despite having had no apparent opportunity to exchange information or energy due to the finite speed of light. This phenomenon suggests that these distant regions were once in causal contact, a notion that contradicts the limitations imposed by the universe's age and the speed at which light travels. This conundrum strikes at the core of the Big Bang Theory's assumptions about causality and interaction. According to the classical model, the universe expanded so rapidly after the Big Bang that regions now far apart could never have influenced each other. Without such interaction, it seems impossible for these areas to share such uniform temperatures. The horizon problem thus raises fundamental questions about the initial conditions of the universe and whether these conditions alone can account for the observed homogeneity without invoking additional mechanisms. To resolve this dilemma, cosmologists developed the theory of cosmic inflation. This groundbreaking theory proposes that, in the universe's earliest moments, an exponential expansion rapidly stretched space itself, driving once neighboring regions far apart at speeds exceeding the speed of light. This expansion would have smoothed out temperature variations, leading to the remarkable uniformity observed in the cosmic microwave background. Crucially, inflation implies that all regions of the universe were once close enough to interact and equalize their conditions before this explosive growth phase. While cosmic inflation elegantly addresses the horizon problem, it also introduces new questions about the exact nature of inflation, how it began, what drove it, and how it ended. Scientists continue to probe these mysteries through a combination of precise observations and advanced theoretical modeling, seeking to refine and validate this powerful concept. Closely related is the flatness problem, which focuses on the large-scale geometry of the universe and its origin. According to Einstein's general relativity, the universe's spatial curvature can be open, closed, or flat, depending on the total density of matter and energy it contains. Remarkably, current astronomical data reveal that the universe is extraordinarily close to flat, meaning its density nearly matches the critical threshold needed to produce this flat geometry. This delicate balance is puzzling because any deviation in density early on would have caused the universe's curvature to dramatically diverge over time. Understanding why the universe is so finely tuned to flatness remains a central challenge in cosmology, one that cosmic inflation theory also helps to explain by rapidly driving the universe toward this balanced state. Together, the horizon and flatness problems, alongside the continued enhancements in detect technology and computer modeling, highlight the dynamic and ever-evolving nature of cosmological research. Each discovery and theoretical breakthrough pushes the boundaries of our understanding, bringing us closer to unraveling the profound mysteries of how our universe came to be and how it continues to change. However, if we turn our gaze back to the earliest moments of the universe, an intriguing puzzle emerges, one that has challenged cosmologists for decades. The universe's density, which determines its overall geometry and fate, needed to be balanced with astonishing precision right after the Big Bang. Even the slightest deviation from a very specific value, known as the critical density, would have had dramatic consequences. If the universe's density had been just a bit lower than this critical threshold, it would have expanded so rapidly that space itself would have stretched endlessly, leading to an open universe that grows forever apart. Conversely, if the density were even marginally higher, gravity would have eventually pulled everything back together, causing the cosmos to collapse in a cataclysmic implosion, ending in a singularity. Yet, our current observations reveal a universe that is remarkably flat, meaning its density is almost perfectly balanced on this cosmic knife edge. This paradox is what physicists call the flatness problem. Why is the universe so finely tuned to this delicate balance? How did it achieve such a near-perfect flatness over billions of years? The answer, as it turns out, might lie in a fascinating and groundbreaking theory known as cosmic inflation. According to the inflationary model, the universe underwent an extraordinary phase of rapid expansion just fractions of a second after the Big Bang, expanding faster than the speed of light. During this brief but explosive growth spurt, any initial curvature or irregularities in the fabric of space-time were stretched out, much like how the surface of a balloon smooths out as it inflates. This expansion effectively flattened the geometry of the universe to an extraordinary degree, erasing the unevenness that might have existed before. After this intense burst of inflation, the universe continued to expand, but at a more measured pace, preserving the near-flat geometry we measure today with remarkable precision. This elegant explanation not only resolves the flatness problem, but also deepens our understanding of the universe's earliest moments and the conditions that shaped its large-scale structure. Understanding why the universe is so flat has far-reaching implications beyond pure geometry. It influences how we think about the ultimate fate of the cosmos, the mysterious nature of dark energy that drives the acceleration of expansion, and the formation of galaxies, stars, and clusters. This ongoing quest to decode the universe's early conditions continues to push the boundaries of science, highlighting the power of theories like inflation in piecing together our cosmic origins. Alongside the flatness problem, another fascinating mystery stems from the predictions of particle physics and cosmology, the magnetic monopole problem. In classical electromagnetism, as established by James Clerk Maxwell's seminal equations, electric charges are known to exist as fundamental sources of electric fields, appearing as isolated positive or negative charges. However, magnetic fields are always observed as dipoles, magnets with both a north and a south pole bound together. Magnetic monopoles, hypothetical particles possessing only a single magnetic charge, either north or south, would fundamentally alter our understanding of electromagnetism. They would represent a new type of particle with profound implications for physics. The magnetic monopole problem arises from certain grand unified theories and inflationary models that predict magnetic monopoles should have been created abundantly in the early universe. As the universe cooled and underwent phase transitions shortly after the Big Bang, these monopoles could have formed as topological defects in the underlying quantum fields, much like cracks forming in freezing ice. Yet, despite decades of searching, no magnetic monopoles have ever been observed. This discrepancy between theory and observation presents a compelling puzzle. If magnetic monopoles were indeed produced in vast quantities, where are they now? The inflationary theory offers a possible solution here too. By rapidly expanding the universe, inflation would have diluted any primordial monopoles to such an extent that their presence would be almost impossible to detect today. Thus, the magnetic monopole problem not only challenges our understanding of particle physics, but also reinforces the significance of cosmic inflation in shaping the universe we see. Together, the flatness and magnetic monopole problems form crucial pieces of the cosmic puzzle. They reveal the intricate dance of forces and particles in the universe's infancy and the extraordinary mechanisms that led to the cosmos as we know it, a vast, nearly flat, and mysteriously expanding expanse, still holding secrets waiting to be uncovered. However, extensive cosmological observations, especially those focused on the cosmic microwave background radiation and the large-scale structure of the universe, have consistently failed to detect magnetic monopoles. This absence presents a profound challenge to the theoretical frameworks that predict their existence, raising one of the most intriguing puzzles in modern physics, the magnetic monopole problem. Why do these predicted particles, fundamental to many grand unified theories, seem to be missing from our universe? Magnetic monopoles are hypothetical particles that carry a single magnetic charge, either north or south, unlike ordinary magnets which always have both poles. Theoretical physics suggests that in the early moments after the Big Bang, phase transitions in the universe's cooling process should have produced a significant number of these monopoles. Yet, despite decades of searching through cosmic data and particle experiments, they remain elusive. This puzzling absence forces scientists to reconsider their understanding of the universe's infancy and the validity of their models. One implication of this dilemma is that our grasp of phase transitions in the early universe might be incomplete. These transitions, analogous to water freezing into ice, are thought to have shaped the fundamental forces and particle contents of the cosmos. If the predicted monopoles are missing, it suggests either the physics governing these transitions requires refinement or that some unknown process suppressed the production or survival of monopoles. Among the theoretical proposals to solve this puzzle, cosmic inflation stands out as a particularly elegant explanation. Inflation theorizes that the universe underwent a period of extraordinarily rapid exponential expansion in the fractions of a second after the Big Bang. This dramatic growth would have effectively diluted the concentration of any existing monopoles, stretching them so thinly across space that their current density would be far too low to detect. In this way, inflation reconciles the absence of monopoles with the initial theoretical predictions that they should exist. Yet, inflation's role in addressing the magnetic monopole problem is just one piece of a larger story. The theory also provides solutions to other long-standing cosmological mysteries. For example, the horizon problem, which asks why distant regions of the universe appear strikingly uniform despite being too far apart to have ever exchanged information at the speed of light, is resolved by inflation. Before this rapid expansion, these regions were in close proximity, allowing them to homogenize. Inflation then stretched these tiny uniform patches across vast cosmic distances, explaining the remarkably even temperature of the cosmic microwave background radiation observed today. Inflation similarly addresses the flatness problem, which concerns the surprising observation that the universe's geometry is incredibly close to flat. Initially, the universe could have had positive curvature like a sphere or negative curvature like a saddle. But the inflationary expansion stretched space so profoundly that any initial curvature was smoothed out, much like a balloon's surface appears flatter as it inflates. This explains why the cosmos looks so close to the critical density needed for flatness, a feature that standard Big Bang theory without inflation struggles to justify. The ongoing search for magnetic monopoles is more than just a quest to find a missing particle. It holds the potential to reshape our understanding of fundamental forces and the unification of physical laws. Finding direct evidence of monopoles would be groundbreaking, confirming predictions about the nature of magnetism and potentially unveiling new layers of reality tied to the unification of gauge symmetries in particle physics. In essence, the magnetic monopole problem highlights the dynamic nature of theoretical physics and cosmology. It embodies the tension between elegant theoretical predictions and stubborn observational realities. This challenge propels scientists to refine their models and develop new insights, illustrating the relentless human drive to comprehend the universe at its deepest levels. As the story of cosmic inflation and magnetic monopoles unfolds, it continues to illuminate the remarkable journey from the chaotic dawn of time to the structured cosmos we observe today. Moreover, the concept of cosmic inflation offers a compelling resolution to the long-standing magnetic monopole problem that has puzzled cosmologists for decades. In the early universe, magnetic monopoles, hypothetical particles with a single magnetic pole, were predicted to form in significant quantities. Yet, despite thorough searches, these monopoles have never been detected, posing a critical challenge to conventional Big Bang theory. The inflationary model proposes that a period of extremely rapid expansion, occurring fractions of a second after the Big Bang, would have stretched space so dramatically that any monopoles present were diluted to such low densities they became practically invisible to our instruments. This dilution process provides a coherent explanation for the absence of monopoles in today's universe, suggesting that although these particles may have been created, their presence was thinned out beyond detection during the inflationary epoch. But cosmic inflation is more than just a solution to this particle mystery. It addresses several fundamental puzzles that the standard Big Bang model could not adequately explain. For instance, it sheds light on the remarkable uniformity observed in the cosmic microwave background radiation, the afterglow of the Big Bang, which appears nearly identical in all directions. Without inflation, it is difficult to understand how regions of the universe so far apart could have come to such a homogeneous state given the limits imposed by the speed of light. Inflation proposes a mechanism for rapid exponential growth that smoothed out any irregularities, effectively stretching the fabric of space and ensuring regions now separated by vast distances were once close enough to exchange information and energy. This theory also tackles the flatness problem, the question of why the geometry of the universe appears so close to perfectly flat, rather than curved or warped. By rapidly expanding space, inflation drives the universe toward flatness in much the same way that blowing up a balloon makes its surface appear flatter as it grows larger. Consequently, inflation integrates and unifies these major cosmological observations into a single framework, enhancing our understanding of the universe's earliest moments and its subsequent evolution. Today, it remains a cornerstone of modern cosmology, continually tested and refined as researchers push the boundaries of observational astronomy and theoretical physics. However, despite its successes and widespread acceptance, inflation is not without competitors. Several alternative theories have been proposed that attempt to solve the same cosmological puzzles without invoking a phase of rapid exponential expansion. One notable contender is the class of non-singular bounce models. Instead of beginning with a singular Big Bang, a point of infinite density and temperature, these models suggest the universe undergoes cycles of contraction followed by expansion. In this bouncing scenario, the universe contracts to a finite size before bouncing back, beginning a new expansion phase. This cyclical process avoids the problematic singularity that traditional Big Bang theory entails, while also offering explanations for the observed uniformity and flatness of the universe. Because regions of space are connected prior to the bounce, these models ensure causal contact between distant areas, addressing the horizon problem without inflation. Another fascinating alternative is the ekpyrotic model, which draws on concepts from higher dimensional physics. According to this idea, our familiar three-dimensional universe is one of two branes existing within a higher dimensional space. The collision of these branes produces a hot, dense state that evolves into a universe much like ours. This model explains the large-scale homogeneity and isotropy of the cosmos through the dynamics of the brane interaction rather than rapid expansion, offering a radically different geometric perspective on cosmic origins. By focusing on brane collisions rather than inflationary expansion, the ekpyrotic scenario presents a novel approach to the initial conditions that set the stage for the universe's growth. Further still, modified gravity theories explore alternatives to inflation by revisiting the fundamental nature of gravity itself. These theories suggest that at extremely large scales or under early universe conditions, gravity may not behave exactly as predicted by Einstein's theory of general relativity. Instead, slight modifications could produce effects that mimic those traditionally attributed to inflation, such as smoothing out inhomogeneities or driving accelerated expansion. Researchers in this field are deeply engaged in attempting to reconcile quantum mechanics with classical gravitational theory, striving to create a more unified and comprehensive description of the cosmos. Modified gravity remains a dynamic and evolving area of study, challenging standard paradigms and expanding the frontiers of cosmological thought. In sum, cosmic inflation stands as a powerful explanatory tool that has reshaped how scientists understand the early universe, resolving some of the most profound questions in cosmology. Yet, the continued exploration of alternative models like bounce cosmologies, the ekpyrotic scenario, and modified gravity highlights the vibrant and ongoing quest to unravel the true origins and behavior of our universe. Each theory brings its own insights and challenges, underscoring the complexity of the cosmos and the depth of human curiosity driving the pursuit of knowledge. Lastly, topological defect models offer a captivating glimpse into the early moments of our universe, proposing that it may have contained extraordinary irregularities known as cosmic strings or domain walls. These enigmatic defects are not merely theoretical curiosities, they could have played a profound role in shaping the universe's evolution. According to these models, such defects might have helped generate the vast cosmic structures we observe today, galaxies, clusters, and the intricate web of matter spanning billions of light years. They could also explain the subtle temperature fluctuations etched into the cosmic microwave background radiation, the faint afterglow of the Big Bang. Remarkably, these effects might be accounted for without invoking an inflationary phase, a rapid expansion period that is a cornerstone of the widely accepted inflationary cosmology. While inflation elegantly resolves many cosmic puzzles, including the universe's uniformity and flatness, these alternative topological defect theories continue to inspire rigorous research and spirited debate. Each model offers unique mechanisms and perspectives that deepen our understanding of the universe's origins and the fundamental forces at play, illustrating how cosmology remains a dynamic and evolving field of scientific inquiry. In parallel, the steady-state theory presents a bold challenge to the conventional Big Bang narrative, proposing an alternative vision of a universe that is eternal and essentially unchanging. Unlike the Big Bang model, which posits a singular, explosive beginning followed by continuous evolution, the steady-state framework emphasizes permanence through perpetual matter creation. According to this view, even as the universe expands, new matter is continuously formed, ensuring that the overall density remains constant over time. This theory finds its strength in the concept of cosmic homogeneity, the observation that the universe appears remarkably uniform no matter where or when we look. Proponents argue that this uniformity is best explained not by a singular origin event, but by ongoing creation that balances expansion with fresh matter filling the gaps. They question several fundamental aspects of the Big Bang model, including the interpretation of the cosmic microwave background radiation. While the Big Bang theory treats this radiation as a relic from a hot, dense early universe gradually cooling over billions of years, steady-state theorists propose that this glow might arise from alternative processes, such as light scattering through intergalactic dust and gas. They also explore different nuclear pathways for the formation of light elements, suggesting these could form in space over extended periods rather than during a brief primordial event. Despite its innovative approach, the steady-state theory has gradually faded from mainstream acceptance, largely due to mounting observational evidence supporting the Big Bang paradigm. Discoveries such as the precise measurements of the cosmic microwave background's uniformity, the detailed mapping of the universe's expansion rate, and the observation of large-scale cosmic structures have all reinforced the Big Bang model's explanatory power. Yet the rigorous debates between supporters of these theories have propelled cosmology forward, sharpening scientific methods and deepening our grasp of cosmic history. While the steady-state model no longer holds sway in contemporary cosmology, its legacy endures as a crucial chapter in the evolving story of how humanity understands the cosmos. Turning our gaze toward the future, modern scientific models suggest a variety of intriguing possibilities about the ultimate fate of the universe, each hinging on key cosmic parameters like the rate of expansion, the total amount of matter, and the mysterious influence of dark energy. One widely discussed scenario is the so-called Big Freeze. In this vision, the universe continues to expand forever. Galaxies drift apart, and over unimaginable spans of time, the cosmos grows colder and darker. Stars burn out as their nuclear fuel is exhausted, galaxies lose their brightness, and the universe fades into an increasingly silent and frozen state. Another possibility is the Big Crunch, a dramatic reversal of cosmic expansion where gravity's pull eventually halts and then reverses the universe's growth, causing everything to collapse back into an incredibly dense hot singularity. Though compelling in theory, current observations suggest this fate is unlikely, as the universe's expansion appears to be accelerating rather than slowing. Perhaps the most striking and unsettling prediction is the Big Rip. If dark energy continues to drive accelerated expansion at an ever-increasing rate, it could eventually tear apart the very fabric of space-time. Galaxies would be torn asunder, stars would be ripped from their orbits, planets destroyed, and ultimately, even atoms and subatomic particles themselves could be pulled apart. This cataclysmic ending would unravel every structure in the cosmos, leaving behind an unimaginable void, a universe stripped down to its most fundamental nothingness. These diverse and dramatic scenarios underscore how much remains to be discovered about the cosmos, reminding us that the story of the universe is far from complete. Each theory, observation, and debate is a step on humanity's ongoing journey to comprehend the vast, mysterious expanse we call home. Finally, some scientific models dare to entertain the fascinating notion of cyclic universes, grand cosmic realms where the universe does not just have a beginning and an end, but instead undergoes endless, rhythmic cycles of expansion and contraction. Each cycle could be uniquely different, creating an intricate and ever-changing cosmic tapestry. These ideas open a window into some of the deepest, most profound questions about existence itself and the nature of time. They serve as a humbling reminder that, despite the tremendous knowledge we have gained about the universe, our understanding remains far from complete. The full cosmic story is still waiting to be told. One of the most compelling visions of the universe's distant future is known as the Big Freeze. Rooted firmly in cosmology, this concept paints a picture of a universe that keeps expanding forever. As space stretches, galaxies drift further and further apart, causing temperatures to drop and the overall energy density of the cosmos to decline over unimaginably long timescales. Over billions of years, the nuclear fuel that powers stars will gradually run out. As stars fade and new ones fail to form, the night sky will dim, galaxies will grow dark, and the universe will slowly drift into a vast, cold silence. This slow and steady decline casts an eerie shadow over the ultimate fate of everything around us. The Big Freeze suggests that the universe will one day reach a state of extreme entropy, a kind of cosmic equilibrium where matter and energy are spread evenly throughout space, leaving nothing but darkness. Stars will burn their final cores, galaxies will drift into solitary isolation, and the universe will grow colder and darker with each passing epoch. Eventually, what remains will be a ghostly realm dominated by white dwarfs, neutron stars, and black holes, celestial relics in a fundamentally lifeless expanse. As time stretches even further into the distant future, even these remnants will cease to exist. Neutron stars might survive for billions of years more before fading away, while black holes slowly lose mass through a mysterious quantum process called Hawking radiation. In this far-flung era, the cosmos will be a vast emptiness filled with incredibly thin, diffuse particles spread across an unimaginable void. The Big Freeze offers a sobering, almost poetic reflection on the relentless march toward a universe stripped of warmth, light, and life. A silent testimony to the impermanence of all things. At the heart of this cosmic drama lies dark energy, a mysterious and elusive force that shapes the future of the universe. Dark energy makes up about 70% of the total energy content of the cosmos, yet it remains one of the greatest puzzles in modern physics. Scientists believe it acts as a repulsive force, counteracting gravity's pull and driving the accelerated expansion of the universe we observe today. This invisible energy stretches the very fabric of space, pushing galaxies apart at ever-increasing speeds. Thanks to dark energy, the universe is likely to keep expanding indefinitely, leading to the chilling scenario of the Big Freeze, where galaxies become ever more isolated. As dark energy spreads space wider and wider, it also makes star formation increasingly rare by diluting the gas and dust necessary to birth new stars. The stretching of space itself prevents meaningful cosmic interactions, slowly freezing the universe into an unchanging, cold expanse. But dark energy also challenges our understanding of physics at the deepest levels. Its nature and origin remain shrouded in mystery, and scientists are actively searching for a theory that can explain its properties. Some theories even suggest that dark energy might change over time, altering the universe's expansion rate in unpredictable ways. If that happens, it could dramatically reshape cosmic destiny, potentially leading to scenarios far stranger and more violent than the Big Freeze, like the Big Rip, where the fabric of reality is torn apart, destroying galaxies, stars, and even atoms. In this unfolding cosmic saga, dark energy plays a starring role. It shapes the evolution of the cosmos and forces us to confront profound questions about the universe's fate and our own place within it. As research continues and we inch closer to understanding this enigmatic force, we may unlock secrets that redefine our comprehension of existence itself. Another possible ending to this grand story is the Big Crunch. Unlike the endless expansion of the Big Freeze, the Big Crunch imagines a universe where expansion eventually reverses. This could happen if the total density of matter in the universe, both visible matter and the mysterious dark matter, exceeds a critical threshold. If there is enough mass, gravity's pull could overcome the outward push of dark energy. In such a scenario, the universe's expansion would slow, stop, and then reverse direction. Galaxies, stars, and all matter would be drawn ever closer in an enormous cosmic collapse. Over time, everything spirals inward toward a single point, a singularity of infinite density where all matter and energy converge. This dramatic gravitational implosion would mark the end of one cosmic cycle, potentially setting the stage for the birth of a new universe. The Big Crunch highlights the delicate balance of cosmic forces that determine our universe's fate. Whether the universe will expand forever, collapse back on itself, or perhaps cycle endlessly through expansion and contraction remains one of the most captivating questions in cosmology. The answers lie deep within the fabric of space and time, challenging our understanding and inspiring new generations of scientists to explore the mysteries of the cosmos. However, current observations have brought significant challenges to the long-standing Big Crunch theory about shaking the foundations of how we once imagined the universe's ultimate fate. For decades, scientists speculated that the universe, after expanding from the Big Bang, might one day stop and reverse course, collapsing inward in a catastrophic event known as the Big Crunch. Yet the latest astronomical data paints a far different picture. Astronomers have discovered that the universe is not just expanding, it is accelerating in its expansion. This unexpected acceleration is primarily attributed to a mysterious force called dark energy, an invisible phenomenon that permeates space and pushes galaxies apart with ever-increasing speed. This discovery, which earned the 2011 Nobel Prize in Physics, drastically reduces the likelihood that the universe will ever halt its expansion to contract again. Supporting this view, scientists have gathered compelling evidence from two critical sources: distant exploding stars known as supernovae and the cosmic microwave background radiation, the afterglow of the Big Bang itself. The light from these distant supernovae acts like cosmic mile markers, revealing how quickly space is stretching over time. Meanwhile, the uniform glow of the cosmic microwave background provides a snapshot of the infant universe, allowing cosmologists to track its evolution across billions of years. Together, these data streams strongly suggest that the cosmos will continue to expand indefinitely, drifting toward a future far removed from a dramatic collapse. While the Big Crunch remains an intriguing theoretical possibility within certain frameworks, the weight of evidence now favors scenarios in which the universe's expansion persists. This paradigm shift leads to alternative cosmic endings, such as the Big Freeze or the Big Rip. The Big Freeze envisions a universe growing colder and emptier over time as stars burn out and galaxies move beyond each other's reach, while the Big Rip speculates a violent, eventual tearing apart of all matter driven by ever-intensifying dark energy. The study of these possible futures highlights the dynamic and evolving nature of cosmology, a science continually reshaped by new discoveries and observations. It reflects humanity's enduring quest to understand not only the origins of the universe, but also its eventual destiny. One concept closely tied to this unfolding cosmic narrative is the heat death of the universe. Heat death describes a distant future when the cosmos reaches a state of maximum entropy, meaning energy is spread evenly throughout space and no usable energy remains to fuel any kind of work or activity. As the universe expands and ages, stars exhaust their nuclear fuel and cease to shine, matter cools down and temperatures approach absolute zero, the coldest possible temperature where atomic motion nearly stops. In such a scenario, the once intricate and vibrant structures of galaxies, stars, and planets gradually dissolve, leaving behind a sparse cosmos filled with fundamental particles scattered across vast, dark expanses. Heat death symbolizes the end of all energetic processes. Star formation halts, galaxies drift apart irreversibly, and the universe fades into darkness. The remnants of stellar life, white dwarfs, neutron stars, and black holes will endure for an unimaginably long time, but even they are not eternal. Over billions and trillions of years, neutron stars are expected to disintegrate, and black holes will slowly evaporate through a quantum mechanical process called Hawking radiation. This slow but certain decay will ultimately leave the universe as a nearly empty void, devoid of light, heat, or activity. In this bleak but scientifically grounded future, physical processes like chemical reactions and biological functions become impossible. Life, as we understand it, could no longer exist. This sobering prospect invites profound reflection on the nature of existence itself, reminding us that all cosmic structures, no matter how magnificent or enduring they seem, are subject to the relentless laws of thermodynamics. The concept of heat death brings into focus the vastness of cosmic timescales, far exceeding human comprehension. The current era, rich with star formation and luminous galaxies, will eventually come to an end. Scientists estimate that star formation will continue for about 10 trillion more years, a staggering span compared to the mere 13.5 years since the Big Bang. Massive stars, which live fast and die young, will exhaust their fuel and explode as supernovae within tens to hundreds of millions of years, leaving behind dense neutron stars and black holes. Meanwhile, smaller stars like our Sun, with lifespans of roughly 10 billion years, will slowly burn their fuel and fade into white dwarfs. Once the last stars flicker out, the universe will enter an unimaginably long phase of cooling and dimming. White dwarfs will gradually lose heat over trillions of years, transitioning into a theoretical state called black dwarfs, cold, dark remnants that no longer emit significant light or heat. This transformation alone could take about 100 trillion years, an almost incomprehensible stretch of time that dwarfs the universe's current age. As we peer into the distant future, this cosmic timeline reveals not just the fate of stars and galaxies, but the eventual quiet dissolution of all matter and energy as we know it. The universe's destiny, shaped by mysterious forces and governed by physical laws, serves as a profound reminder of the transient nature of everything within it. from the smallest particle to the grandest galaxy. Understanding this fate challenges us to reflect on the beauty and fragility of existence itself, inspiring awe at the cosmic journey from fiery beginnings to a silent, cold end. Ultimately, as the universe ages over countless trillions of years, it will dwindle into a silent, almost empty expanse. The once vibrant cosmos, teeming with stars and galaxies, will be reduced to only isolated remnants. Primarily black holes and a sparse scattering of cold particles drifting in the vast void. Even black holes, often thought to be eternal, are predicted to slowly evaporate through a mysterious process known as Hawking radiation. Over unimaginable timescales, these cosmic giants will fade away, dissolving into nothingness long after the last stars have burnt out and ceased to shine. This timeline offers a sobering glimpse into the distant future, a slow and deliberate unraveling of the stellar fabric that once illuminated the universe. It is a future both awe-inspiring in its sheer scale and profoundly quiet, where time stretches endlessly and the universe's grandeur softly dims. The Big Bang Theory, which describes the universe's explosive birth from an incredibly dense and hot state, has not only revolutionized modern cosmology, but has also deeply influenced religious and philosophical thought. This groundbreaking concept has sparked a re-evaluation of humanity's understanding of existence, creation, and the cosmos itself. For many religious thinkers, the idea of a singular cosmic beginning resonates strongly with ancient narratives about creation, stories where the universe emerges from a definitive moment of origin. The notion that the cosmos began at a specific point in time aligns with theological concepts that the universe is not eternal, but instead has a distinct starting point. This alignment has led some scholars of faith to explore ways in which the Big Bang Theory complements traditional beliefs about divine creation, seeing science and spirituality as intertwined paths toward truth. On the other hand, the Big Bang Theory also presents challenges and raises profound questions for certain religious viewpoints. The scientific explanation, grounded in natural laws and observable phenomena, prompts debates about the role of a creator deity in a universe governed by physics and randomness. The vastness and apparent indifference of the cosmos can be unsettling, stirring philosophical dilemmas about purpose, free will, and the presence or absence of a higher power. Philosophically, the Big Bang ignites deep inquiries into the nature of existence and reality. It pushes us to question what, if anything, existed before the universe came into being, and whether time itself is merely a construct that began with the Big Bang. These questions challenge long-held ideas about causality, infinity, and the fabric of reality, inviting philosophers into intricate discussions about the origins of everything and our place within it. As scientific knowledge advances, the dialogue between cosmology and philosophy continues to flourish, weaving a rich tapestry of ideas and perspectives. This intersection encourages both scientists and theologians to engage in thoughtful discourse, reflecting humanity's timeless quest to understand the universe and our relationship to it. Beyond the realm of academia, the Big Bang Theory has left a significant mark on popular culture, reshaping how we view the cosmos and our place within it. The dramatic story of the universe's origin has inspired countless documentaries, films, books, and television shows, sparking widespread public fascination with astronomy and cosmology. One notable example is the popular television sitcom named after the theory itself, which humorously portrays the lives of scientists and embraces nerd culture. By weaving scientific ideas into everyday conversation, it has helped bring complex concepts about the universe closer to the general public's understanding. In literature, the Big Bang has inspired authors to explore profound themes about existence, time, and the cosmos. Science fiction writers, in particular, use the universe's creation as a backdrop to imagine futures, alternate realities, and the very nature of reality itself. This fusion of science and storytelling invites readers to ponder life's mysteries, destiny, and the cosmic forces that shape everything. Visual art, too, has been influenced by the Big Bang, with artists creating stunning installations and exhibits that interpret cosmic phenomena. Utilizing cutting-edge technology, these works depict the vastness and drama of space, making the complex science accessible and emotionally resonant for viewers. Through such creative expressions, the grandeur of the cosmos becomes tangible and inspiring. In sum, the Big Bang Theory stands not only as a pillar of modern cosmology, but also as a catalyst for cultural, philosophical, and spiritual exploration. It reminds us of our deep, innate curiosity about the universe and connects us through a shared sense of wonder. Our understanding of the universe's origin, especially through the lens of the Big Bang, has fundamentally transformed how humanity perceives existence, time, and our cosmic place. Once thought to be eternal and unchanging, the universe is now recognized as a dynamic, evolving entity with a definitive beginning. This shift in perspective fosters a profound sense of connectedness, linking all matter, from distant galaxies to the atoms in our bodies, back to a common origin. These insights reach beyond science, prompting existential reflections about our very being. The realization that we inhabit a universe born from a singularity invites us to rethink traditional notions of time, causality, and the infinite. By suggesting that time itself may have begun with the Big Bang, this narrative entwines the story of the cosmos with our own human curiosity and quest for meaning. Moreover, this profound understanding has sparked a cosmic humility within humanity, compelling us to confront our relative smallness against the vast backdrop of the universe. As we peel back the layers of space and time, unraveling the staggering scale of the cosmos and the intricate processes that govern its evolution, we come to see Earth as nothing more than a tiny speck adrift in an immense cosmic ocean. This recognition does more than simply humble us. It deepens our appreciation for the fragile planet we call home and the delicate web of life it supports. In embracing this perspective, we awaken to a profound responsibility, one that urges us to protect the environment and safeguard the diverse forms of life that share this pale blue dot with us. This awakening invites us to ponder the grand narrative of existence, compelling us to grapple with fundamental existential questions that have shaped human thought for millennia. The unfolding story of the universe's origins bridges the realms of science and philosophy, challenging us to expand our worldview and rethink our place within the cosmos. It transforms our relationship with the universe into one marked by awe and curiosity, igniting a relentless desire to explore and understand the mysteries that lie beyond our reach. Scientific revelations, such as the Big Bang Theory, not only illuminate the universe's beginnings, but also introduce critical ethical considerations that challenge how we view ourselves and our responsibilities. As we learn that all matter, ourselves included, emerged from a singular cataclysmic event, a profound sense of unity with the cosmos takes root. This unity fosters a collective sense of stewardship over our planet, emphasizing the need for ethical treatment of the environment and the preservation of the fragile ecosystems that sustain life. The vastness of the universe, filled with seemingly endless possibilities, compels us to consider our treatment of life beyond Earth. As humanity advances in space exploration and contemplates inhabiting other worlds, we face ethical dilemmas about our interactions with extraterrestrial environments and potentially alien life forms. The consequences of our actions may reverberate far beyond Earth, demanding a comprehensive ethical framework that considers the long-term impact on the cosmos and generations yet to come. Reflecting on the universe's origins also leads us to profound questions about meaning and purpose. The pursuit of knowledge, while essential, carries with it ethical responsibilities. Every scientific breakthrough must be weighed against its potential consequences, whether technological advancements that could benefit humanity or risks such as environmental harm or the creation of dangerous technologies. Navigating this delicate balance requires guiding our scientific endeavors toward outcomes that promote the well-being of all life. Our growing understanding of the universe's birth reshapes not only our cosmic perspective, but also invites a deeper ethical dialogue about existence, responsibility, and our interconnectedness within the vast web of life. This ongoing conversation is vital as we confront the implications of our discoveries and strive to honor the complexity of the cosmos while securing a sustainable future for all living beings. The Big Bang Theory has been instrumental in transforming our perception of humanity's place in the cosmos. By revealing that the universe began as a singular, extraordinarily hot and dense state, scientists have shown that everything, from the most distant galaxies to the stars that light our skies, and ultimately to ourselves, shares a common origin. This interconnectedness challenges earlier views that placed humans at the center of the universe, demonstrating instead that we are an intrinsic part of a grand cosmic story, shaped by the same forces that forged celestial bodies. As our understanding of the universe expands, it becomes clear that Earth is just one small planet orbiting an average star, nestled within an unremarkable galaxy among billions of others. This humbling revelation demands a reassessment of our significance, reminding us that the universe operates on scales and complexities far beyond human concerns. Yet within this vastness, our existence remains remarkable, a testament to the extraordinary circumstances that brought forth life and consciousness in an otherwise immense and indifferent cosmos. Furthermore, delving into the mysteries of our cosmic origins sparks some of the deepest philosophical questions humanity has ever faced. Questions about our purpose, our meaning, and the very nature of existence itself. Many people wrestle with the idea that the vast universe, with all its wonders and complexities, can be explained entirely through natural processes. This leads to intense debates. Is meaning something already woven into the fabric of the cosmos, or is it something we as conscious beings must create on our own? The realization that we are literally made of stardust, atoms forged in the fiery hearts of ancient stars, does more than just connect us physically to the universe. It places us within a vast, interconnected story that stretches across billions of years. Our individual lives become threads woven into the grand narrative of stars being born, living out their lifespans, and eventually exploding in spectacular supernovae, scattering the essential elements for life across the cosmos. The Big Bang Theory revolutionizes how we see ourselves in this enormous universe. Once, many believed humanity occupied a central, predetermined role in creation. Now we understand ourselves as active participants in a dynamic, ever-evolving cosmos. This shift encourages an insatiable curiosity, urging us to explore, discover, and continually seek knowledge not just about the universe, but also about ourselves. It fosters a profound sense of wonder and a responsibility to reflect on our place and role in the sprawling tapestry of existence. As our understanding of the Big Bang expands, it reveals surprising and meaningful connections with many scientific fields, including biology. While cosmology focuses on the origin and evolution of the universe, it also provides the essential backdrop for understanding how life itself became possible. In the earliest moments, the universe was a hot, dense sea of fundamental particles and radiation. As it expanded and cooled, the simplest elements, hydrogen and helium, formed, setting the stage for the creation of stars, galaxies, and eventually planets. Within these first stars, nuclear fusion fused lighter elements into heavier ones. When these stars ended their lives in colossal supernova explosions, they scattered vital elements like carbon, oxygen, and nitrogen throughout the cosmos, elements that are the building blocks for the complex molecules essential to life. This cosmic cycle reveals the intimate link between the universe's grand evolution and the delicate emergence of biology on planets like our own. Moreover, the study of the Big Bang intersects intriguingly with astrobiology, the scientific search for life beyond Earth. Researchers examine distant exoplanets to assess whether they formed under conditions similar to those that allowed life to flourish here. Understanding the physical and chemical aftermath of the Big Bang offers crucial clues in identifying potentially habitable worlds, shaping our quest to determine if life might exist elsewhere in the universe. In essence, the story of the Big Bang is not just a tale about the birth of stars or galaxies. It is the foundation of all life and a catalyst for humanity's ongoing journey to understand the cosmos and ourselves. It invites us to imagine, explore, and contemplate the profound mystery of life's place in the vast universe, inspiring new generations to ponder what it truly means to exist. Additionally, the exploration of the cosmos carries profound philosophical implications that intertwine deeply with biological questions surrounding the origins of life and intelligence. This grand quest to comprehend our place within the vast expanse of the universe invites not only scientific inquiry, but also profound reflection on the very nature of consciousness, adaptation, and evolution. Here, an extraordinary interdisciplinary dialogue emerges, where cosmology, biology, geology, chemistry, and other scientific fields converge, enriching our understanding of existence itself. This confluence of knowledge reveals the intricate and interconnected pathways through which life first emerged and eventually thrived across eons. The study of the Big Bang, the monumental event marking the universe's birth, fuels collaboration between a diverse array of scientific disciplines. It enhances our understanding of how the primordial conditions shaped the emergence and evolution of life, while simultaneously sparking deeper philosophical questions about our origins and what it means to exist. Geology, for instance, serves as a vital link connecting the cosmic past with the tangible history of our planet. By unlocking the secrets of the early Earth, geology extends our grasp beyond the universe to the processes that crafted a cradle for life itself. Scientists delve into the ancient rock formations and geological processes that have preserved traces of Earth's earliest epochs. These ancient stones act as time capsules, offering a rare glimpse into the environmental conditions that defined our planet's formative years. From these clues, researchers reconstruct the dramatic transformation of Earth from a molten, inhospitable sphere into a dynamic, life-supporting world. One critical focus lies in understanding the planet's internal structure and composition. Through the process called differentiation, heavier elements sank inward to form Earth's core, while lighter materials floated upward, creating the mantle and crust. This geological sorting reveals much about the early solar system's conditions and informs our knowledge of how Earth's atmosphere and hydrosphere took shape. Volcanic activity played a significant role in shaping Earth's early atmosphere, releasing gases that contributed to its chemical makeup. Extraterrestrial materials, such as comets and meteorites, also delivered essential elements, enriching Earth's primordial environment. Among geological features, banded iron formations stand out as crucial records. They provide compelling evidence about the early atmosphere's composition and the rise of oxygen levels during a period known as the Great Oxygenation Event. This dramatic increase in atmospheric oxygen, driven by photosynthetic organisms, marked a turning point in Earth's history, establishing the conditions necessary for the evolution of complex and diverse life forms. By carefully analyzing these geological records, scientists gain invaluable insights into the circumstances under which life might arise on planets formed long after the Big Bang. In a wider cosmic context, geology intersects with cosmology by offering clues to planetary formation and evolution across the solar system and beyond. The processes that molded Earth are not unique, but rather echo across other terrestrial planets and moons, scattered throughout the cosmos. Through the field of comparative planetology, informed by geological studies, we recognize that understanding Earth's geology enhances our ability to discern the conditions necessary for life on other worlds and guides the ongoing search for exoplanets with similar histories. Thus, geology provides a vital piece of the cosmic puzzle, connecting the story of Earth to the broader narrative of the universe. This interplay between geological processes and cosmic events deepens our understanding of how life and worlds coalesce within the ever-evolving tapestry of the cosmos. At the heart of this cosmic narrative, chemistry plays an indispensable role in deciphering the mysteries of the first elements that arose in the aftermath of the Big Bang. By unraveling the formation, properties, and significance of these primordial elements, chemistry sheds light on the early universe's evolution. In the moments following the Big Bang, the universe consisted mainly of fundamental particles, protons, neutrons, and electrons. As the universe expanded and cooled, these particles began to combine, initiating the formation of the first atomic nuclei in a process known as Big Bang nucleosynthesis. This remarkable phase, which lasted only a few minutes, created the lightest elements, primarily hydrogen and helium, along with trace amounts of lithium and beryllium. The principles of nuclear chemistry, which govern the interactions of atomic nuclei, enable scientists to decode the specific reactions that produced these primordial elements. By examining the present-day ratios of these elements in the universe, researchers test theoretical models leading to a profound understanding of the conditions that prevailed in those earliest moments. This fusion of chemical and cosmological knowledge ultimately illuminates the universe's infancy and lays the foundation for the complex cosmic structures and life itself that would emerge over billions of years. Moreover, chemistry offers us an extraordinary window into the universe's earliest moments, by enabling us to explore how the very first elements behaved, interacted, and transformed over billions of years. At the heart of this cosmic story lies hydrogen, the simplest and most abundant element in existence. Hydrogen played a pivotal role in the birth of stars, those brilliant furnaces that not only illuminate the cosmos but also forge heavier elements through the powerful process of nuclear fusion. By delving into the chemical reactions occurring within stars, scientists gain vital insights into how essential elements such as carbon, oxygen, and iron were created, laying the foundation for the complex chemistry that would eventually nurture life itself. The reach of chemistry extends far beyond just stellar interiors. It also serves as a cornerstone for astrophysics, particularly in the analysis of light emitted or absorbed by distant celestial bodies. Through a technique called spectroscopy, scientists can decode the elemental makeup of stars and galaxies, unlocking secrets about the ongoing processes of element formation and transformation across the vast universe. These spectral fingerprints allow researchers to reconstruct a detailed narrative of the universe's elemental evolution, revealing how the original hydrogen gas seeded the formation of stars, galaxies, and ultimately the diverse matter that fills the cosmos. In essence, chemistry acts as a vital bridge connecting cosmology, the study of the universe at large, and the emergence of complex matter. By explaining the behavior and interactions of the universe's first elements, chemistry enriches our understanding of the cosmic saga, illustrating how the universe's beginnings set the stage for the rich and varied tapestry of matter and life we observe today. Mathematics, too, holds a fundamental place in unraveling the mysteries of the early universe. It provides the essential language and framework for describing physical phenomena, analyzing data, and predicting the behavior of cosmic events. The complexities involved in the universe's origin and growth demand highly precise mathematical formulations to capture the intricate interplay between matter, energy, space, and time. Using mathematical equations and models, scientists interpret observations, quantify cosmic properties, and explore the consequences of different theoretical possibilities. Among these mathematical tools, one of the most crucial frameworks is Albert Einstein's theory of general relativity. This groundbreaking theory uses sophisticated mathematical constructs to describe how mass and energy interact with the very fabric of spacetime through gravity. The equations of general relativity enable scientists to trace how the universe expanded from a singular point in the Big Bang and to understand how gravity shapes the vast cosmic structures we see today. This mathematical foundation also allows researchers to predict key aspects of the universe's evolution, including its expansion rate and the curvature of space. Mathematics also proves indispensable in modeling specific early universe events such as primordial nucleosynthesis. By applying differential equations, scientists simulate the extreme conditions shortly after the Big Bang, when light elements like hydrogen and helium formed. These mathematical models predict the amounts and masses of these elements, which can then be compared to astronomical observations, refining our understanding of those primordial moments. Beyond modeling, statistical methods and probability theory play a vital role in analyzing data gathered from telescopes and other astronomical instruments. Mathematics helps cosmologists assess the likelihood of various cosmological models in light of new evidence, fostering an ongoing dialogue between theory and observation. This iterative process guides scientists toward the most accurate descriptions of the universe's current state and its dynamic history. Taken together, mathematics is not merely a tool, but a necessary framework that empowers us to decode the early universe's mysteries. Through mathematical principles and techniques, scientists assemble the cosmic puzzle of origins, gaining profound insights into the fundamental processes that shaped the cosmos. Mathematics transcends disciplinary boundaries, harmonizing with empirical science to expand our knowledge of the universe's evolution. Recent breakthroughs in particle physics, cosmology, and quantum mechanics have pushed our understanding of the Big Bang theory even further. A striking example comes from particle accelerators like the Large Hadron Collider. Here, scientists recreate conditions akin to those just fractions of a second after the Big Bang by colliding particles at unimaginably high energies. These experiments reveal the fundamental building blocks of matter and the forces that govern their interactions, providing invaluable glimpses into the universe's earliest chapters, when all matter and energy were compressed into a hot, dense state. In this way, the combined efforts of chemistry, mathematics, and cutting-edge physics unite to illuminate the profound journey from the universe's fiery birth to the vast cosmos teeming with stars, galaxies, and life that we explore today. Moreover, breakthroughs in quantum mechanics have dramatically deepened our understanding of how the universe began, tracing its origins back to an unimaginably dense and scorching hot state. At the heart of this cosmic dawn lie quantum fluctuations, fleeting, microscopic shifts in energy that occur on the tiniest scales of reality. These ephemeral ripples may have been instrumental in shaping the universe's infancy, planting the very seeds from which galaxies, stars, and the vast cosmic web eventually emerged. Scientists now believe that these subtle quantum jitters acted as the blueprint for the sprawling large-scale structures we observe scattered across the heavens today. Peering into the earliest moments of existence, researchers use insights from quantum theory to piece together a narrative of creation that is as intricate as it is awe-inspiring. Beyond theory, cutting-edge observational tools have further solidified our cosmic story. Technologies designed to study the cosmic microwave background radiation, a faint, ancient glow left over from the universe's fiery beginnings, provide a unique window into the past. This subtle afterglow carries with it detailed information about the temperature and density variations present shortly after the Big Bang, effectively serving as the universe's own fingerprint. By meticulously analyzing this radiation, scientists gain a clearer picture of how the universe expanded and how matter was distributed over billions of years. What's truly remarkable is the way interdisciplinary collaboration fuels this quest for knowledge. Astrophysicists, quantum physicists, cosmologists, and engineers all work together, combining their expertise to unlock the mysteries of the cosmos. Every discovery builds upon previous layers, gradually revealing a richer, more coherent story about how the universe unfolded from chaos into complexity. As these fields evolve and cross-pollinate, our understanding grows more nuanced and profound, opening new pathways to explore the very fabric of reality. Yet, despite the tremendous progress, profound questions linger at the frontier of cosmic science. One of the greatest enigmas is the precise mechanism behind cosmic inflation, the astonishingly rapid expansion that the universe experienced moments after its birth. While inflation theory elegantly accounts for the remarkable uniformity observed in the cosmic microwave background, the specific physical triggers behind this colossal growth spurt remain elusive. Scientists tirelessly search for the fundamental particles or energy fields that could have driven this explosive phase, hoping to uncover clues that lie beyond the reach of current models. Adding to the mystery are the shadowy components known as dark matter and dark energy. Together, they dominate the cosmic makeup, with dark matter constituting about 1/4 and dark energy roughly 70% of the total universe. Yet, their true nature remains one of the most puzzling challenges in physics. These invisible forces not only shape the structure and behavior of galaxies, but also dictate the ultimate destiny of the cosmos itself. Understanding who or what these elusive entities are and how they sculpt the universe's evolution is vital to unlocking the next chapter in our cosmic story. Delving even deeper into the beginning, the very conditions at the origin point of the Big Bang, possibly a singularity where space and time themselves converge, pose profound puzzles. The laws of traditional physics struggle to describe the extreme state of matter and energy that must have existed then. Questions about how time itself began, or whether the Big Bang was truly the start of everything, or merely a transition within a grander cosmic cycle, continue to challenge our most fundamental assumptions about reality. Moreover, the striking imbalance between matter and antimatter in the universe remains a significant riddle. According to current theories, the Big Bang should have produced equal amounts of matter and antimatter, which would have annihilated each other, leaving behind a cosmos filled only with light. Yet, the observable universe is overwhelmingly composed of matter. Unraveling the physical processes that led to this asymmetry is crucial, as it explains why stars, planets, and ultimately life exist at all. Among other intriguing quests, the search for the cosmic neutrino background offers a tantalizing glimpse into the earliest cosmic epochs. Similar in concept to the cosmic microwave background, this relic radiation consists of neutrinos, tiny, nearly massless particles that flooded the universe moments after the Big Bang. Detecting these neutrinos is extraordinarily difficult, as they interact very weakly with matter, slipping through ordinary detectors unnoticed. However, advances in technology and experimental design are opening new possibilities for capturing their elusive signals. One promising method involves placing highly sensitive detectors deep underground, where they are shielded from cosmic rays and other interfering radiation. These detectors use large volumes of water or ice as targets. When a neutrino interacts with the medium, it can produce faint flashes of light called Cherenkov radiation. Specialized sensors capture these brief glimmers, providing indirect evidence of neutrino interactions. Another innovative approach focuses on supernova neutrinos, particles emitted in staggering numbers when massive stars explode. Some of these neutrinos may have origins tracing back to the primordial universe. By studying these cosmic messengers, scientists hope to glean insights about the cosmic neutrino background and the conditions of the universe's earliest moments. As humanity continues to push the boundaries of knowledge, each discovery not only enriches our understanding, but also deepens the mysteries that inspire us to look further. The universe's origins remain one of the greatest stories ever told, a testament to human curiosity and the relentless pursuit of truth across the vast expanses of space and time. Furthermore, groundbreaking experiments such as those carried out by the IceCube Neutrino Observatory in Antarctica are at the forefront of capturing high-energy neutrinos, elusive particles that hold clues to some of the universe's most energetic and mysterious cosmic events. These experiments primarily focus on detecting neutrinos originating from phenomena like supernova explosions and active galactic nuclei, powerful centers of galaxies thought to harbor supermassive black holes emitting intense radiation. However, the data collected from these ventures go beyond the immediate sources. They may eventually unlock secrets about the cosmic neutrino background, a faint, pervasive sea of neutrinos thought to have filled the universe since its infancy. As scientists continuously refine their detection methods and develop increasingly sophisticated experimental setups, the once intangible goal of observing this subtle cosmic background grows steadily more achievable, promising to reveal unprecedented insights into the earliest moments of the cosmos. One of the most daunting challenges in modern astronomy is the quest to observe the universe's first generation of stars, commonly known as population 3 stars. These stars are believed to have formed just a few 100 million years after the Big Bang, during an epoch aptly named the Cosmic Dawn. Unlike the stars we see today, population 3 stars were likely enormous, intensely hot, and lived very brief lives compared to their successors. Unfortunately, their light has long since faded, making direct observation extraordinarily difficult. To detect them, scientists turn to cutting-edge technology and inventive observational strategies. Among these, the deployment of powerful space telescopes stands out. The recently launched James Webb Space Telescope exemplifies this leap forward. It is equipped with highly sensitive instruments designed to detect faint infrared light, which can penetrate the cosmic dust and gas that veil the early universe. By focusing on infrared wavelengths, the telescope can peer deeper into space and further back in time than any previous instrument, aiming to uncover the earliest galaxies and potential signals from those ancient first stars. Beyond direct detection, researchers also examine the after effects left by these primordial stars, studying how their intense radiation altered the surrounding intergalactic medium. This involves analyzing specific signatures in the emission and absorption lines of hydrogen and helium, the universe's most abundant elements, in far-flung galaxies. When the light from the first stars interacts with the surrounding hydrogen gas, it leaves telltale fingerprints that scientists can detect even today. By piecing together these indirect clues, astrophysicists can reconstruct the history of population 3 stars formation and their impact on cosmic evolution. Simulations and theoretical modeling are equally crucial in this pursuit. By examining data from younger stars and galaxies closer to us, researchers can refine their models to better understand the conditions that would have allowed the first stars to ignite. These models help predict where and how to search for evidence of these ancient giants, guiding future observations. As observational technologies continue to improve and our knowledge of the universe deepens, the mystery of the first stars moves closer to resolution, holding the promise of unlocking invaluable information about the origins and evolution of the cosmos. Parallel to the search for ancient stars, improving measurements of the cosmic microwave background, CMB, remains a cornerstone in cosmology. The CMB is the relic radiation left over from the Big Bang, offering a snapshot of the universe just 380,000 years after its birth. Precise observations of the CMB allow scientists to delve into the universe's early conditions and trace its subsequent evolution. To enhance the accuracy and detail of CMB measurements, several innovative approaches and technologies are being pursued. One significant strategy involves the development of next-generation detectors with unparalleled sensitivity. These instruments are engineered to capture minute fluctuations in the CMB's temperature and polarization with exceptional resolution. Space-based missions, such as the upcoming NASA PICO satellite, aim to circumvent the distorting effects of Earth's atmosphere by operating from the pristine environment of space. Freed from atmospheric interference, these telescopes can obtain clearer, more detailed observations of the CMB's subtle signals. Cutting-edge technologies like superconducting circuits in detectors promise to further amplify scientists' ability to sense the faintest variations in the ancient microwave light. Ground-based observatories also play a vital role in advancing CMB research. Large-scale facilities like the Atacama Cosmology Telescope in Chile and the South Pole Telescope in Antarctica are dedicated to mapping the CMB with extraordinary sensitivity. These observatories combine innovations in instrumentation and sophisticated data processing techniques to extract meaningful patterns from the complex tapestry of the CMB. Their work complements space-based efforts, ensuring that every possible angle is explored to unlock the secrets hidden in the oldest light we can observe. Together, these endeavors, whether capturing neutrinos from cosmic phenomena, chasing the faint glow of the first stars, or refining measurements of the cosmic microwave background, are pushing the boundaries of our understanding. They are piecing together the grand story of the universe's origins and evolution, revealing a cosmos far richer and more intricate than ever imagined. The fusion of machine learning and advanced statistical techniques is rapidly transforming the way scientists analyze data from the cosmic microwave background radiation, or CMBB. These cutting-edge methods are capable of processing enormous volumes of data, far beyond what traditional analysis could handle, allowing researchers to uncover faint, intricate patterns hidden within the cosmic signals. By refining cosmological models with this newfound clarity, these innovations offer a powerful synergy that stands to revolutionize our understanding of some of the most profound questions in cosmology. How old is the universe? What is it made of? And what forces are responsible for its continual expansion? As technology marches forward, the drive to capture ever more precise measurements of the CMBB will unlock a treasure trove of cosmic insights. This pursuit not only sharpens our picture of the universe's infancy, but also opens pathways to discoveries that could reshape fundamental physics. One of the most tantalizing prospects lies in the potential detection of new particles, entities predicted by theories that extend beyond the familiar standard model of particle physics. Take supersymmetry, for example. This theoretical framework proposes that every known particle has a yet undetected heavier counterpart, superpartners like the selectron or squark. Finding these elusive particles could illuminate mysteries such as the nature of dark matter, a mysterious substance that makes up roughly 27% of the universe, but remains invisible to direct observation. Supersymmetric particles might also shed light on how the universe evolved in its earliest moments, influencing its structure and composition in ways we are just beginning to understand. Another exciting line of inquiry involves axions, hypothetical particles that emerge from efforts to solve puzzles related to the strong nuclear force, which binds atomic nuclei together. If axions exist, They might constitute the elusive dark matter, influencing the cosmos in profound ways right after the Big Bang. Detecting axions requires highly sophisticated experiments designed to observe their interactions with photons under extreme conditions, such as powerful magnetic fields, a challenge that pushes the limits of current technology. Adding to the intrigue are sterile neutrinos, a proposed class of neutrinos that defy easy detection because they do not engage with either the weak nuclear force or electromagnetic force. Their elusive nature makes them extraordinarily difficult to spot, yet their discovery could explain anomalies in neutrino experiments and offer vital clues about the imbalance between matter and antimatter in the universe. Meanwhile, primordial gravitational waves, ripples in the very fabric of space-time created during the universe's earliest epochs, offer a unique window into the Big Bang itself. Unlike particles, these waves carry direct information about the processes unfolding at the universe's birth. Current and future missions aim to measure the CMBB with unprecedented precision, searching for subtle signals left behind by these ancient gravitational waves. Confirming their existence could fundamentally alter our understanding of how the universe began, providing a direct glimpse into its most formative moments. But the quest does not end with the Big Bang. Scientists are pushing the boundaries to probe what may have preceded it, despite the immense challenges posed by limited observational data. One promising approach is studying cosmic inflation, a theory proposing that the universe underwent a brief but extraordinary expansion immediately after the Big Bang. By analyzing the intricate details imprinted on the CMBB, researchers hope to uncover signatures of this inflationary epoch, potentially revealing the physical conditions before the universe burst into existence. Detecting primordial gravitational waves tied to inflation is another key strategy. These waves would create distinctive patterns in the polarization of the CMBB. Instruments capable of detecting such patterns could not only validate critical aspects of inflation theory, but also unveil new information about the energy scales and forces active before the Big Bang. This could revolutionize our understanding of the early universe, offering clues about the fundamental physics that shaped everything we see today. Together, these groundbreaking explorations of particles, waves, and cosmic signals stand at the frontier of modern cosmology. Each discovery carries the potential to deepen our grasp of the universe's origin story, challenging and expanding the scientific narrative about the cosmos itself. The synergy of advanced technologies, theoretical insights, and relentless curiosity continues to propel humanity toward unraveling the grandest mysteries of existence. Additionally, physicists are delving into fascinating theories known as cyclic or bouncing universe models. These concepts suggest that our universe is not a one-time event, but part of an endless cycle, continuously expanding and then contracting in a grand cosmic rhythm. Imagine the universe as a cosmic heartbeat, pulsing through phases of growth and collapse. To explore these ideas, scientists create detailed simulations that mimic conditions before what we call the Big Bang. They aim to recreate scenarios where the universe we live in today could be the result of a previous contraction phase, a cosmic rebound from a past collapse. These cyclic models are not just abstract theories, they make concrete predictions. For example, they might explain specific patterns in the way galaxies and vast cosmic structures are arranged across space. By examining the distribution of galaxies or looking for subtle signals in the cosmic microwave background, the faint afterglow of the Big Bang, researchers hope to find evidence supporting these cycles. Such observable phenomena could serve as critical tests, helping to confirm or challenge these revolutionary ideas. Meanwhile, advancements in particle physics are offering another window into the universe's earliest moments. Using particle accelerators, scientists recreate conditions similar to those just fractions of a second after the Big Bang by colliding particles at extremely high energies. These experiments can reach energy levels comparable to those in the infant universe, allowing physicists to study the fundamental forces and particles that shaped everything around us. Through these high-energy collisions, researchers probe states of matter and energy that existed before the universe settled into its current form, providing clues about what might have come before the Big Bang. As research in cosmology and particle physics advances hand in hand, our understanding of what happened before the Big Bang grows richer and more detailed. Each new discovery adds threads to the intricate tapestry of cosmic history, unveiling fresh pathways toward answering one of humanity's oldest questions: where did our universe truly begin?